everyone. Welcome to the fourth NCI and Intersect showcase, AI and Machine Learning in Astrophysics. Before we start, I'd like to acknowledge the traditional owners of countries throughout Australia, their diversity, histories, knowledge, and their continuing connections to land and community. We pay respects to all Australian Indigenous peoples, their cultures and their elders, past, present and emerging. My name is Chris Power. I'm a Senior Principal Research Fellow at the International Centre for Radio Astronomy Research at the University of Western Australia. My research tackles dark matter and galaxy formation theory using supercomputer modelling. I will be the moderator for today's showcase. Now, let's welcome Satish Nair, the CEO of Intersect, to make some opening remarks.
Thanks, Chris. Good day, everybody, and a warm welcome to today's showcase. My name is Satish Nair, and I'm the CEO at Intersect, a co-host of today's event. Today's showcase is the fourth in a series of educational sessions that Intersect and NCI are collaborating on to provide further focused education for postgraduate level researchers. The subject of today's showcase is fascinating as we often look up to the sky and wonder at its expanse. It's of particular interest to all those who are keen in learning about the use of AI and ML in understanding the working of the cosmos and unraveling new physics. I would like to thank the speakers for their time in sharing their knowledge, inspiring research, and raising awareness in this field. Also, a special thanks to Nugent from Intersect for her work in organizing this event. I'll not take any more time and hand over the chair of today's showcase, Professor Chris Power.
Thank you, Satish, for the opening remarks. In the showcase today, we are very fortunate to have four excellent speakers, internationally recognized for their leadership in AI and machine learning in astrophysics. But before I go on to introduce our first speaker, a little bit of housekeeping. Each of our speakers will be presenting for 50 minutes, followed by a 10-minute Q&A session. If you have questions for the speaker, you can enter them into the Q&A tab. During the Q&A, I will read out the questions to the speaker. Audience members can also ask their questions by using the raise hand emoji at the bottom of the screen. They will need to wait for their name to be called and the host will unmute them. Last but not least, the speakers have kindly agreed to have a 20-minute panel discussion after the last talk. This will be a chance for you to ask additional questions based on everything that you hear today. So now it's my great pleasure to introduce our first speaker, Salman Habib. Salman is the director of the Argonne National Laboratory's Computational Science Division and an Argonne Distinguished Fellow. He uses large-scale supercomputing to attack problems in cosmology, including advanced statistical methods applied to complex inference problems. Over to you, Salman.
Well, thank you very much, Chris. And I would also like to thank Mayun for all the effort that has gone into this. And I'm very happy to be here. And good morning, everybody. And I'll start the screen sharing. And hopefully this will all work. There we go. So hopefully everyone is seeing everything. This is all good. So cosmology as an arena for AI and machine learning seems like a slam dunk, right? Because everything in AI and machine learning is essentially based on a huge amount of data, and cosmology by definition is everything. So it's the data of everything. However, there's more to it than that, of course. So let's dive into it. Okay, so the very first question before we begin talking about cosmology as an arena for AI/ML is obviously what is the whole point of AI and machine learning in science? Like, why precisely is science different? Because we're all familiar with AI and machine learning, obviously, in natural language processing and in vision, but the big difference is that data is not easy to get in science. Data acquisition is not cheap. You don't just have it for free on the internet. There are significant infrastructure costs. There's also a very important point, which is the data in good shape? Do we really understand what our data is telling us? What kind of, do we really have the calibration issues sorted out and so on? So curation of the data is almost as important as the data itself. Moreover, we are not just interested in classification or certain very specific classes of machine learning or AI problems. we're often interested in teasing out pretty subtle inferences from the data stream. And that may not be a simple thing to do. The other interesting thing is that data and computing go hand in hand in solving scientific problems. So we are often interested in using modeling and simulation as well as just looking at data. So it's an interesting interplay of both of these fields. The other important point in science is that we obviously want to get the right answer, and we are not happy if the answer is sometimes right and sometimes wrong. So rigorous uncertainty quantification, what people in the business call UQ, is often of great interest to us, and scientists are naturally dubious about black box methods, so that's something that's important to us. The other important thing is that a lot of the work that goes on in machine learning and AI is actually looking at correlations and not necessarily at causal structures. So this is something that concerns scientists quite a bit, because you want to understand why did something happen, what happened earlier, what happened later, how are all of these things connected? And how can we go from one place to the other if data is missing? How can we deal with counterfactuals? So these are important questions that are very specific to science. Finally, science is a very complex blend of theory, modeling, and associated data. It's also a blend of biases. Scientists feel like we need to understand something. Now, what it means to understand varies from person to person, but it is something that is a deeply held belief. So this makes the applications of AI and ML methods also somewhat context dependent. What works in one area may not work in another area. What may not be natural for things to transfer. That said, there is very significant enthusiasm for incorporating AI/ML methods in the scientific enterprise, and this has happened over the last few decades as data has come in, as technology has improved, and has been highly accelerated over the last few years, as with AI methods like which we're all well familiar with. But let me give one example just to get sort of our sort of point of view kind of straightened out. So let's say that we're doing an optical survey and we can find something like 10 billion objects. And out of these, there is some interest in maybe pulling out 1,000 interesting objects. Maybe these are strongly lensed objects or strongly lensed galaxies that we wish to find. Now, 10 billion is a lot. I mean, it's not easy to just train people to look at 10 billion objects. So let's say that we do have an AI method, that's good. Then we have to figure out, well, how good is it really? So let's assume that follow-up cost for 1,000 objects is something like $5 million. So that's something you can imagine getting. But if you want to pick out these 1,000 objects from 10 billion, naively speaking, you require an accuracy of what I would call 7 nines, meaning 1 part in 10 million, sorry. And even if your method was 99.9% accurate, this would be terrible, because you would still be off by many orders of magnitude, in the sense that you can't possibly look up as many objects as this method gives you, because you wanted something that was 7 nines accurate. So often we are interested in a level of classification accuracy in an unsupervised setting that is just very difficult. So this gives you an example of what kind of requirements we might have over the traditional kind of users of AI that you see. So the next question you might have is, you might say, well, cosmology sounds like a very complex business. So, how difficult is such a task going to be? Well, cosmology, and so here's a slide which is somewhat of a digression, but it's kind of a comparison of cosmology and climate, because these are in some sense have some similarities and some differences. So both are observational sciences. So we are concerned with inverse problems and issues of data assimilation. Both involve known physics, because we are not inventing any brand new physics necessarily, in the sense that we have models for both of them. We don't have to understand our models, because certainly in cosmology, we don't really understand what the dark matter is or what dark energy is doing. But we have mathematical models that we can use. Both have high dynamic range in space and time. Both face end-to-end modeling problems, meaning complex problems that we have some initial condition and go somewhere with it. Both deal with emergent phenomena, meaning that you start with very simple equations, but very complex things emerge from them. And both have to deal with very large and complex data sets. However, cosmology actually turns out to be much simpler in some sense, because we have no external energy and other drivers. We have a much simpler information flow. There are no feedback loops, strange things happening. On large scales in cosmology are only weakly coupled with small scales. And moreover, we are only interested in a small number of key issues, whereas climate researchers are concerned about many complicated things. So finally, cosmology is now precision science. We're interested in nailing down some things to a very high level of precision and accuracy, sub-percent, in fact. And that's, of course, very different from climate. Climate is not there yet, but it's getting there. And often in cosmology, we're interested in relatively coarse-grained summary statistics, although that is changing, and not so for climate, where climate may be concerned with small-scale things, including microclimate kind of issues. So cosmology, in some sense, is a simpler problem. So let's now explore the AI/ML context in cosmology. But before I go there, I just want to quickly thank all of my collaborators. It's been a lot of fun working on these problems for something like 25 years now, and it's been great working with people. And I think one of the very nice things about cosmology is it's a very broad area, and people can contribute in many different ways, which is one of the great kind of fun pieces of working on cosmology. Okay, so now let's focus on cosmology itself. So as I said already, it's an observational science, but it is different in the sense that we have only one data sample. We have only one universe, so we have to be thinking about, okay, how does that make life different? Of course, it's complex in a multi-physics, multi-scale sense. A lot of stuff is happening. We have to worry about scales from sub-parsec all the way to gigaparsec. And progress in cosmology relies on new methods of observation and new methods of combining multiple types of observation. And at the moment, we have seen a huge, I would say, revolution in cosmological data from the Sloan Digital Sky Survey and 2DF, which obviously was in Australia. And these surveys of the sky in multiple wavelengths, a sample of these surveys is on the right of this slide, will deliver and have delivered enormous amounts of data in the hundreds of petabytes of multispectral imaging. So the size and complexity of the data sets already forces you to think in terms of machine learning and AI methods. It's simply not possible to do anything else. And the other interesting thing is, because the data we have so much of the data and so much of the analysis uses summary statistics, that the statistics is already very, very good. And the problem is not that we don't have enough data, which used to be historically the problem. The problem is we don't know what to do with it. And we are, in some sense, modeling limited. So the question is, can AI and ML help us overcome this? So in order to do this, we require new research in AI foundations, methods, and uncertainty quantification in this context. So I'll try to say a few more things about that. But before I get there, I want to show in a set of images exactly what I mean when I say so much statistical information is available. So if you go and look at the Sloan Digital Sky Survey, and this was a set of data when the survey wasn't complete, but nonetheless, if you look at a piece of the survey, and I'm going to click on this, and each time I'm going to be focusing on one point in the sky, but you can see this was the survey. All of these things, all of these points are essentially galaxies and some stars. But now we're going to zoom in, and you can see there's a whole bunch of galaxies here, and we continue zooming in. And this, we could have zoomed in anywhere, but we happen to be zooming in to a particular spot, which is, of course, the Whirlpool galaxy, M51. Many of you would be very familiar with this. So the important point I want to show in this set of zooms is that we could have gone anywhere, and this is thanks to David Hogg, we could have gone to anywhere in that picture, and we would have seen the same amount of information. So there's an enormous amount of information that cosmological surveys have, and it's our job to figure out what it's trying to tell us. So this brings us to the next question of what precisely is modern cosmology anyway. And I'd like to say that the cosmology now is a study of the universe as a dynamical system. And so we like to propose and test laws governing the dynamics of a large-scale universe. We want to understand, what the matter content is, what the geometry is, how its universe is evolving. And we want to propose and test theories of initial conditions, primordial fluctuations. And we want to understand all these mysteries that many of you are familiar with, obviously, like what is the dark matter, what is dark energy, what are the mechanisms by which primordial fluctuations were generated. And one very interesting thing is that since cosmology has become so solid as a field, we can actually use it as a probe of fundamental physics. For instance, it's the best method now to figure out what is the sum of neutrino masses. So it's kind of amazing that a universe as a dynamical system can enable you to get all of this. And this is a huge change, So this cartoon here is basically shows Lev Landau, the famous physicist, who made a remark that cosmologists are often wrong, but never in doubt, which may have been true a long time ago, but certainly isn't true anymore. And the reason for this is that the field has changed significantly and is now in a very sort of controlled situation. We know exactly what we're doing. That doesn't mean that we understand it, but it does mean that we can model it and we can observe it very carefully. So let's repeat once more the situation we are in, which is that cosmology is an observational science, which means that it's not experimental physics. And I say this because this is one of the reasons why machine learning and AI methods are so important. In areas where we can isolate on things that we want to study, and we can experimentally isolate the system, we can try many different things. Those are the requirements of precision measurement. Controllability, repeatability, isolation, that's not available in cosmology. We can't really say, oh, let's make a universe that we like and check out what's happening there. So our budgets aren't big enough for that. So, and the observations are often dictated by circumstances, and they're not, you can see what you can from the ground. There's the atmosphere in the way, et cetera, et cetera. You do the best you could. And so you have to do a lot of cross-checks to eliminate systematic errors, for example. Sometimes the cross-checks may not be available. Sometimes the theorist may be screwing up. Sometimes the modeling may not be accurate enough. So it is just a complicated business. And we also, the other important point is that the cosmological standard model, as I said, is full of uncertainty in the sense that the model works quite well. Lambda CDM as a model works really well. But we don't have any fundamental guidance of exactly why does the model work. I mean, why is the dark energy consistent with a cosmological constant? Why is the dark matter acting as if it has no other interactions except gravitational? So these are deep questions. And so the only thing we can do is just try to make do with the data, or make best use of the data that's available. So cosmology now is fundamentally the study of sky maps. And the history of sky maps, obviously, this comes from astronomy, is Hipparchus with his 850 fixed stars in 129 BC. And this was a key source of astronomical observations for 2,000 years. So it's kind of remarkable, actually. But then after that, after we got telescopes and so on, then I think at the next stage of very large data is the Palomar Sky Survey on the 48-inch, which gave you roughly 1 billion objects. And ever since then, as I mentioned already, 2DF, SDSS, we are, with hundreds of millions of galaxies, and there's any number of modern surveys. So the important point is that we have views of the universe in different wavelengths. And the question is, what do we do with them? So that takes us to an interesting spot in cosmology where we have a large amount of data. And I wanted to say, where exactly do simulations feed into this as well? So what exactly is the role of data and what is exactly the role of simulation? So first, let's kind of think about where data and statistics enter, because that's crucial to machine learning and AI applications. So first of all, even though we have only one universe, it has lots of objects. So we can do, in some sense, data mining activities, hunt for patterns and empirical relationships between objects, even if we don't necessarily understand what's going on. And there are any number of classification, clustering, and regression tasks in this activity, and some of the talks that follow, you will see these in action, so I will not talk about them. There are also very interesting issues of image analysis, like, for example, finding arcs in strong lensing, and understanding and classifying galaxy morphologies, dealing with things like deblending when you have a survey with lots of galaxies, kind of splatting on top of each other, denoising, and all kinds of other technical details that machine learning can help you with. The grandest problem in machine learning and AI for cosmology is the statistical inverse problem of saying, okay, I know what the universe is doing now and maybe a little bit in the past, but how can I use that to reconstruct all the parameters in my standard model? And how can I go back and reconstruct even perhaps the very beginning of the universe in some sense? So this is actually also related to how statistics has, as a field, changed over time. Old school statistics started with limited data like cosmology. And you basically use very simple data models to fit things like linear models. And then in the age of big data with machine learning, you basically decided forget it, I'm not going to use simple models at all. The models are going to be extremely complicated. There's an arbitrary dynamical map that may connect an input to an output. So that's where cosmology is headed. But that is also where AI and large-scale machine learning is headed. So, so let's start with a very, very simple structure formation crash course, because what I'm going to be describing now is structure formation and cosmology is going to play an important role in that. So, and having a good handle on the theory of structure formation in the universe is actually essential for using the precision cosmology probes we have now, which I will not have the time to describe in detail. So I just want to mention the big picture, which is that we start with what we consider known initial conditions, which means that in the far past, the universe was very homogeneous and isotropic, but there were small primordial fluctuations. Then, as the universe expanded, these primordial fluctuations, because gravity is locally attractive, basically blew up, which is called the gravitational Jeans instability. And the instability, if you had a static universe, would grow exponentially, but because the universe is expanding, is diluted and only grow as a power law in time. But that instability then leads to the formation of structure. And on the bottom left of this slide, you see sort of what happens. So Z is redshift, so at very high redshifts or earlier epochs, the universe is very homogeneous, a chunk of the universe from a simulation. And as time goes on, you can see this formation of what is known as the cosmic web, which is that initially what happens is that the initial collapse of the matter is in sheets. The sheets intersect to form filaments, so the filaments intersect to form nodes. That's what we call halos, and then gas falls in and is there, and galaxies form, stars form and galaxies form in these halos. So that's basically how structure forms, or a process called hierarchical structure formation. Small things form first and conglomerate to make bigger things. What's interesting about this is that the early part of the universe, because the density perturbations were small, can be handled by relatively straightforward methods, what some people call linear theory, but it's not as simple as that, but nonetheless, it's relatively straightforward. But once things go nonlinear, you have to use simulations, and you have to basically, there's no way out. If you really want to understand in a deep way how structures form and what is going on, you have to go to the computer. There's no recourse. So now let's take a look at what the situation is in cosmology in terms of observations. So a kind of revolution, I would say, occurred in cosmological observations over the last, starting at around the turn of the century, and then literally within a decade or so after that. So these slides are meant to sort of show you that. So in 1999, I asked Eric Geweiser, I think he was a grad student at the time, to actually compile some results for me from the cosmic microwave background temperature fluctuations, and he did that. So this is on the top left, you can see. So the measurements of the temperature fluctuations barely see the peak in the CMB, right? And in 2013, which is only 14 years later, you have these beautiful results from Planck. It's just amazingly good, right? So that is, in my opinion, a revolution. Now, something similar was happening in optical surveys. If you look at a results compilation of the correlation function of galaxies like to cluster. There's a certain way that clustering happens. They're two-point clustering. The surveys weren't that big. And this famous signal, the baryon acoustic oscillation peak that was observed, this particular observation is from Boss in 2012, was simply not there in the data in 1999. So there has been a massive increase in the sensitivity of CMB observations and galaxy survey observations, obviously. And the interesting thing now is that this is a challenge to simulations to be able to reproduce the statistics, and also, because we want to understand the systematics of what's going on, how structure that is actually formed traces the density field and the velocity field underneath. So what do cosmological simulations have to do in order to sort of address these issues? So the bad news is they have to be really big, which means you have to have a computer with a large amount of memory. A very large spatial dynamic range is needed, because I said you want to go from gigaparsecs to parsecs. Well, that may be difficult, but at least a kiloparsecs, which is still a dynamic range of 1,000,000 to 1. And you need this dynamic range everywhere, because the universe is not, it's kind of has structure pretty much everywhere. You need also a very large dynamic range in mass because you're interested in things that have masses of 10 to the 15 solar masses, for example, for massive clusters, down to 10 to the 11 solar masses for halos in which live galaxies that might be of interest to you. So there's a large dynamic range in mass. Another sort of, 5 to 6 orders of magnitude. So this might seem daunting, but let's try and compare it with some other fields. So the dynamic range in time is not extreme compared to, say, for example, molecular dynamics simulations in condensed matter physics, because the universe is in some sense dynamically young. So we don't have to take a huge number of time steps, whereas they do, because their dynamic range might require them to go from femtosecond to millisecond. Another interesting thing about cosmology is that the computational work can be parallelized very efficiently. So it's closest in some sense to plasma simulations, and unlike dynamical systems. So for example, if I have a simple dynamical system, but I need to resolve very time steps at very fine time scales, it doesn't help me to have a parallel computer, because in a parallel computer, each node is still slow. If I need only a single node but very fast, there's no way to do anything about that. The other thing, as I mentioned already, because we discussed this climate situation, is that complexity is not extreme, unlike the case of climate simulations. The other piece of good news, well, compared to all of this, is that next generation and exascale machines that already exist are extremely well suited for cosmological simulations. So this is, accidentally, this is true, but fortunately for us, it's really helpful. So what can we do with simulations? We have to target them to particular kinds of observations. Those are listed on the right-hand side of the slide. So gravitational lensing, galaxy clustering, et cetera, et cetera, et cetera. So there's lots of interesting observations. That I said, there's a lot of cross-coupling of these observations. But the interesting thing is that in one very large simulation, we can fit an entire survey and we can measure all of these different things. Now, that is easy to state, but the universe is a mess. So here is the Hubble Ultra Deep Field, which again, many of the pictures, many of you have seen. So our job is not only to sort of say, okay, we have points here and there, we have density, fluctuations here and there. We also have to say, well, what kind of, objects are forming? What is their color? What is their spectra, etc. So this is obviously not an easy task. So this is also like time for a small digression, which is the whole business of high performance computing systems and what are now called digital twins. So digital twins is something else you will hear a lot in AI and machine learning. And one of the interesting scenarios now is that if you look at the large scale AI models, they use so much data. In fact, pretty much all the internet data has been dredged and used in the large scale language models, the LLMs. So one of the interesting question is, will the models get better and better over time as you feed them more and more compute? So that's certainly true. We can buy a lot more compute, but are we going to hit a data wall? Because we simply ran out of data the natural world could provide. That's certainly possible, but computers can provide yet more data. So there's this idea that you can have synthetic data generation, and you can train very large-scale AI and ML models based on synthetic data. So what has evolved over time in these supercomputers is that historically they were first designed to solve simple but computationally hard problems like fluid dynamics. I wouldn't call lattice QCD simple, but something like lattice QCD. And over time, what has happened is, as the machines have gotten bigger, is that we have moved over to solving ever more complex problems on these machines, which means that we are doing simulations that actually look very much like the real world. In other words, very much like nature. So not only can we produce things that look very much like what nature produces, but we can also produce things that are in a different universality class. We can actually produce universes or Earth models or whatever that isn't the real Earth, that isn't the real universe, but it's kind of similar. So we can actually produce an enormous amount of data that we can give to machine learning models and say, okay, we're not smart enough to figure out what the heck is going on, but maybe if you feed all this data into a computer, it can come up with an answer. So that's what some people think. I'm not going to get into that argument, but it's pretty clear that having a very large machine able to do realistic simulations is a necessary requirement in the future for AI. So now let me say just one or two words about why cosmological simulations are difficult. The simplest cosmological simulation involves solving a 6-dimensional partial differential equation, which is the Poisson equation. I just put it here on the right-hand side. The solutions are very complex, and you will see exactly why. And it's not easy to reduce this to lower dimensions. It's not very, very hard to do it on a grid because of 6 dimensions, and also because the nonlinear evolution is such that all kinds of bad things happen with grid codes. And we can then add gas physics, and we can add subgrid models that do star formation and also do other things to enable us to get properties of galaxies and so forth. So I don't have time to go into that, but I only just want to make an important point. Just like I pointed to the fact that there's a revolution in observations, I just want to point to the fact there's a complete revolution in how we think about simulations. So in 1969, Bob Dickey said that the universe is far too complicated for us to even think about doing this, but we do this routinely now. So things change over time, and that's important to keep in mind. So here's an example of a simulation that we ran quite a while ago, but this is a block of a simulation, and the actual simulation is something like 16,000 times bigger than this. So this just gives you an idea of the scale of simulations that are run. So the simulation starts, and we are very homogeneous initial condition. Then the way structure forms is almost like smoke settling. That's the way I like to describe it. And I was saying, you see the filaments forming, you see the nodes forming where the halos are, which are the dark matter dominated clumps, and inside those clumps, galaxies are going to form. And then as you come towards the present time of z is equal to 0, you can see the beautiful cosmic web that is also seen very nicely in observations. So this is just to give you an idea of what large-scale simulations are capable of. But of course, this is only the sort of the skeleton of the structure. This is not actually showing you exactly all these galaxies and everything that I was talking about that we should have. So how do we get that? So in order to do sort of forward models for solving inverse problems, meaning have the ability to produce a universe that looks like what we observe, it's not enough just to be able to do simulations of the kind I just described. So what actually has to be done is you have to have a fairly complex process in which running the simulation code is just the first step. After that, there's a bunch of analysis that you have to do. You have to build in models for how galaxies form, what are their properties using merger trees. Then you have to do any number of things about getting realistic images, for example, model what the instrument is going to look like. So it's a very, very complicated end-to-end problem. And in the end, you have to then have a scientific inference framework based on some Bayesian MCMC type approach. What I would like to basically point out is that this entire chain has now been developed to the extent that we can create actual images, simulated images of the sky that look very, very close to actual images for a given telescope. So these two images that you see in the center of this slide are for Magellan. And if you show these to an observer, it takes them a few minutes to figure out which one is actual and which one is simulated. And I won't tell you exactly how they do it, but they can do it. But nonetheless, it's subtle. So the important point is that we can generate synthetic skies that are very close to what the actual observed skies look like. And here's an example. So in a couple of years, we'll have first really good data from the Rubin Observatory's legacy survey of space and time, but we've already simulated it. This is what it's going to look like. So this is a picture from, it's based on a simulation we ran at Argonne, and there was a lot of other data munging, not munging, sorry, but data analysis to get us to what this looks like. At the same time, a very similar analysis was done to make for the Nancy Grace Roman Space Telescope on another simulation run at Argonne, but for the same base n-body simulation, but with a different pipeline for generating the synthetic images. So you can see that so that's the two blocks on the top left. And you can see that the space telescope, which is the Roman Space Telescope image, next to an LSST Rubin Observatory image. So this way we can generate synthetic data sets for different surveys, and then we can sort of do some pre-analysis of what the surveys are going to be looking like. Okay, so that gives you a picture of like where we are right now. So now let's go over and look at the inverse problem. So the raw objects for the inverse problem in cosmology are the sky maps that I had mentioned already. Summary statistics I've already described. So the idea here is that the theory provides a kind of forward model for predicting your summary statistics. And the inverse problem is fundamentally that I know what the summary statistics is. So if I run many different choices of parameters, make sure my answer matches what I know today, then I have figured out what those parameters are. So the tricky part is that if I'm doing something nonlinear, each forward simulation, because there's no way to go backwards in time, the inverse problem that way is unstable. You have to always go forward. Each simulation is very expensive. So you have to figure out a way of doing these runs in which you don't have to waste a day of supercomputer time for a single forward evolution, because that way the problem will become essentially impossible. So how exactly do we do it? So the big picture is this, and this is going to remain stable over time, meaning whatever our methods may improve, but the general idea is very stable. The general idea is that we have multi-wavelength observations coming from different kinds of telescopes. And on the extreme right, on the extreme left, we have large supercomputers, exascale machines now, but definitely post exascale machines, zetascale machines, whatever in the future. And what these machines are doing is they are generating synthetic universes. And based on the data that they have produced, we will make precision oracles, or very fast predictors using machine learning techniques, and I'll describe that in the next few slides. And then those very fast methods can be used to do the analysis that I described, the inverse analysis, using a Markov chain Monte Carlo technique. At the same time, these simulations also generate synthetic skies that look very, very real. So you can check using that your analysis methods on the observations are also correct. You can ask, am I getting a systematic error? Because if I ran a universe slightly different from the one that I think it is, am I getting the right answer, etc. So this supercomputers enable you to do this kind of uncertainty quantification as well, aside from just giving you a method to solve the inverse problem. And the important point here is that machine learning and statistics enters at pretty much every step of going from the observations to generating the summary statistics, to testing all of these things, to applying, Monte Carlo methods, to building these oracles, etc. So it's kind of embedded in the entire way we do science now. There's no getting around it. So one example of what we call a cosmic calibration framework works like you do some initial simulation, and we can say you want to learn what's happening with, say, 10 parameters. Then what we jokingly call Higdon's rule, after Dave Higdon, one of our collaborators, is that you have to run of order hundreds of simulations. And then once you've run hundreds of simulations, you can use data reduction techniques like principal components or variational autoencoders. And then you can choose schemes to do essentially interpolation in high dimensional space. So there's a classic machine learning problem. Typically we use Gaussian processes, but you can use neural networks as well. And using these pretty much standard things have become standard now. They weren't standard when I started doing it. You can actually build an emulator which replaces a simulation step, which normally, as I said, would take you a day, in literally instantaneously with high accuracy. So here's an example of the thing actually working. So this is an old picture, but I think I'd like to show it because it's kind of fun. So this is essentially a replacement of what the calculation is being done is the 2-point correlation function for matter. So this is basically the power spectrum, which tells you which is the Fourier transform fundamentally of a 2-point correlation function. So what we are doing is we are saying, here's the cosmology, which is on the top left. And then we are asking the emulator to tell us what the answer is. And it gives us the answer in milliseconds. And you say, okay, let's plot it and let's see, there it is. So this is something that can be done in milliseconds. So even if you have to call something like this millions of times to do an inverse problem, you can actually solve it in a reasonable span of time, which otherwise you couldn't. So this is a huge win using machine learning methods. And now we may also ask, well, how good are these emulators? So again, I don't want to spend a lot of time, but just to say that, yeah, they're actually rather good. We can get these emulators to work at the percent level. These figures are only meant to show that you can have an emulator, you can test it against a simulation on which the emulator wasn't built. And it turns out, yes, indeed, our uncertainty quantification is very good. We say it's going to be accurate to a couple %, and it is. And then this is just an example of in the early days when we used these emulation-based methods or machine learning-based methods combined with advanced statistics, Bayesian techniques, to basically take Sloan data and to take data from the CMB, from WMAP, and reconstruct cosmological parameters. And so this, of course, now people do many more sophisticated things, but this was just one of the very early examples of using a machine learning technique embedded inside an inverse problem solver. So now I just want to discuss some representative examples of AI and machine learning. I should also mention the field has completely exploded. So I just gave you, in some sense, a general background for why machine learning and AI are so important now in cosmology and more generally in astrophysics and astronomy. And there are like hundreds of thousands of papers now. There is no way to do a review. So I just want to throw out a few examples and say a few things. And so one interesting question about running simulations as a base for machine learning is that the simulations that I pointed out earlier are very expensive. If you really want to do something with a huge amount of dynamic range, there's an issue of how many simulations you can possibly run, because the digital twins, as they are called, are not cheap. So this is very different from, say, just dredging the internet for data, because data is free there, right? But the data that we are generating is not free. So historically, when people do AI and machine learning, they don't worry too much about methods. Well, of course, they do worry about methods, but one of the arguments is always that we really don't care about convergence or how much data we need, because there's so much data that it doesn't really matter what the asymptotics of the convergence is. So that was true a long time ago. It's no longer true, but earlier on, people used to think this way. But in the case of building an emulator where I have to build it on a small number of simulations, I have to use techniques that are actually very parsimonious in that sense. And also I have to think about active learning. Maybe I first build something with only 100 simulations, and then I import some data, and then I realize that, okay, I will need 10 more simulations and I'm good. Whatever it is, there's an interesting question of what kind of sampling strategy should we use in these high dimensional spaces. And I just want to throw this out and say, this is not a solved problem. So anyone who's interested in sampling theory, they should basically say, oh, I have a way around this. So this is just an example. So when we started working in this area, we had a bunch of friends who were statisticians. We still do. And every year or two, we would meet and say, here's a challenge problem for you guys. So we had a certain sampling technique that we used to use. And what we found out was that in a sequential sense, what we would like to do is to run some number of simulations and some more simulations, and then try to see in what way is the answer in the emulator getting better. And we didn't have a coherent theory for how this works. And this turned out to be a PhD thesis. And, we did end up with a method that, for our purposes, had this thing what I call strong convergence. So the point simply that I'm making here is that when you do a lot of expensive simulations, you can't just run them willy-nilly. You have to come up with some interesting strategy for how to sample the space. And this is something that I think is going to become more and more important in machine learning. So something to keep in mind. Another interesting thing that happens is that some simulations are very expensive, but other simulations are not so expensive. So what we would like to be able to do is to transfer the physics of a simulation. Like, let's say we run an expensive hydro simulation, and we want to transfer the physics that we learned from that hydro simulation to a much cheaper gravity-only simulation. So this, again, can be done by using a version of transfer learning. So here an example, which is from Florian Karlsruhe, who's at Argonne, and so I thank him for these slides. So the point basically here is that we can run matched simulations. We can run a hydro simulation and a matched gravity-only simulation. The hydro simulation has a lot of gas properties for each halo, which, of course, the gravity-only simulation, not having any gas, does not. But there's a learning model that you can build, which allows you to go from one to the other. And once that model works, you can take an arbitrarily large gravity-only simulation and use that model to paint, in effect, the gas physics on top of it. And what Florian has shown that actually you can do this rather well, so that you don't have to run a super expensive hydro simulation for some purposes. You can simply use a gravity-only simulation and use these machine learning technologies to actually move from one to the other in a very smooth and differentiable manner, which makes it very useful for other things in the future. So I think this is another one very interesting use of machine learning and something to keep in mind. Another interesting use of machine learning obviously is, okay, if we can emulate summary statistics, well and good, but why not emulate an entire simulation? So obviously it's not a new idea, and people have been trying to do this for a while using what are called generative networks. And the nice thing, if you could do this with generative networks, is that it would make error estimates far easier, because we could just calculate covariances very easily. We could do lots of simulations. We could do direct inference, field level inference, as people call it, against raw observations. The big question, of course, is how accurately can you do this? And there are techniques like UNet or diffusion models now that allow you to build these generative maps. So we can run a bunch of simulations, and then we can train these maps on these simulations, and then we can say, well, how well did you do? So it turns out that if you do qualitative assessments and even some more quantitative ones, they turn out to be fairly reasonable, but there's a vast space of tests. And what you often find, and I don't want to spend too much time here, I just want to make the point, is that you might do well on certain things, but not very well on other things. So, and because we don't quite understand how these things work, what is the internal machinery of these AI methods, it's a bit puzzling, how can we fix this? So this, I think, is another very interesting question underlying the entire world of generative models, which is, how do you know, sufficiently complex space where they're going to work and where they're going to fail? And when we do discover that they fail somewhere, how can we systematically fix it? So this, I think, is an important problem. Another interesting area now, which in large models, is this thing that people call foundation models. So foundation models are extremely large AI models with parameter sizes ranging from the hundreds of millions to the trillions, many, many trillions. And these are based on a deep learning method called a transformer, which I don't have time to describe, but I'm sure other people downstream might talk about transformers. And these are based on data sources, very extensive data sources, collections from many domains, not necessarily science, could be text, could be visual images, could be audio, could be like lots of different things. And there's a generic pre-training of these models followed by, alignments. And there's a fairly generic model which can then be fine-tuned for specific tasks. So the idea is that there's a relatively general model. You want to do something more along the directions you are interested in. Then you don't have to feed it a huge amount of data. You basically feed it a relatively limited amount of data. And because it has some sort of general knowledge, no one is quite clear on what that means, but nonetheless, it might be able to, if what you're asking it to do is well aligned with how it normally, quote unquote, thinks, it might be able to do a very good job, even though you started with a very small amount of data. So a good example of this is, it comes from natural language processing. If you have a large language model and you give it a completely new language, which has never seen before, it turns out that only a small number of instances allow it to do a very good job at translation. So the question is, can this idea of a foundation model be now extended to the science domain? And the answer is yes. And it can be extended to non-text scientific data. There are many examples, which again, I don't have time to describe, but I think this is a fascinating area in the future. Moreover, because it allows for all kinds of multimodal kind of scenarios where you can have objects that in terms of their color, in terms of their position, in terms of their spectra. Moreover, you may know things about these objects from simulations that you don't know in observations. For example, observations, don't know about halos, or they don't know about merger trees, but simulations do. So you can combine simulations and observations in very interesting ways with foundation models. And this is something that we are working on. So I don't have time to explain in detail how it works, but and foundation models are things that are like very hot at the moment. So there's a number of papers in Astro and Cosmology in this area. And so I think as a methodology, it's very interesting. We have to wait and see how it's going to change the field. That has not happened yet, but all kinds of interesting results are coming up. So finally, let me end by giving sort of the big picture, the cosmological perspective on AI/ML. So this was meant to be a relatively, relaxed talk, not going into too many technical details. So let's recap. So as a data-rich science, cosmology is an excellent application. So I feel that was obvious. The fact that we have simulation capability that allows us to actually deal with, not explain, but come up with things that look like the actual data, meaning realistic complexity. We're in a situation that we don't have a hopelessly complex problem, right? It's complex, but not too complex. And so I think having both of these swim lanes, the data swim lane and the high performance computing swim lane available is very useful. There's no question that AI/ML methods have already solved problems that could not be approached otherwise. And in the future, I can only see this expanding. There are many places where these methods can be applied in astro and cosmology space. And indeed, they have to, because there's so much data and so much complexity that there's no way humans can do this. It just has to be done by machines. One of the interesting questions is uncertainty quantification is a big issue because of all black box techniques is a problem. And this is still relatively crude. And we have to kind of figure out how to deal with this. And this, I think, is going to take a lot of effort from the science side. I don't think people in industry care about this so much, but I think from the science side, we do want to worry about it. The other interesting thing is systematic errors. So systematic errors, which are basically a presence of bias due to problems with measurements or modeling uncertainties or how you build the AI/ML technique, are a big issue. And this is also a problem because this is what statisticians call discrepancy modeling. This is a technology that really needs to be improved significantly before we can actually say, yeah, we understand systematics and how to deal with it.
Salman, 2 minutes.
Yeah, thank you. Yeah, I'm basically done. So it's very good timing. So I think the important point is that in order to deal with all of these very important issues, there has to be a combination of physical modeling input into purely database methods. So the AI and ML side gives us a purely database method of looking at the problem, but we can also come at it from the simulation point of view. Now, the problem is that a sufficiently detailed simulation is in effect like magic. It's so detailed that you can't say I understand it. I mean, I know the equations, I wrote them down, the computer solved them for me, but I can just scratch my head and look at it. So we have this interesting situation that we have a model that we completely understand, but in the sense of mathematically, we can solve it, but that doesn't help us, make sense of what the final result is. And on the other hand, we have data, and we have an AI/ML model that tells us very interesting things about the data, but we don't understand. So how to put these two things together, I think, is going to be a huge deal, and it's going to be something very interesting in the future. So large-scale models of both kinds, simulation and data, will definitely open new avenues. I think it's a fantastic field for young people to go into it now. I mean, it's a fantastic field for not even people like me. And you don't have to be young necessarily, but you just have to be curious and be able to set aside your biases and try not to be a theorist and try to dive deep into this thing. And it may be that we might reverse the scenario, and and the question is, if we know enough, we might go once again from being modeling limited, which we are now, to being data limited, because we'll run out of the data that the universe can provide. Well, I hope not, and I think next generation surveys will help us, go farther in that area and not become data limited, and help us solve all these important problems that we want to solve. So with that, I'd like to stop, and thanks very much.
Thank you, Salman. That was great. So it's now time for questions. It's the Q&A session. I can see that the audience hasn't entered anything into the Q&A session tab yet, but I'd invite members of the audience to raise their hands and ask Salman questions. I guess while we're waiting, Salman, you talked about using machine learning to look at kind of summary statistics from cosmological simulations and comparing them to observables.
Right.
And it's clear that that's possible with large n-body simulations, and to some extent with hydrodynamical simulations as well. You can think of things like the CAMELS project. But is there a limit when it comes to doing that with, say, hydro compared to gravity-only simulations, which seems like a more tractable problem?
Well, so I think what we are doing, so we right now have a project, we're running very large hydro simulations, so like sort of a super flamingo-like thing. And I think in principle, yeah, I don't see any reason why not. I mean, the computational power is there to do these kinds of comparisons. But I mean, I'm not quite sure what you meant by that question, but were you referring to these painting techniques that I was talking about, or?
Yeah, I think I'm probably thinking more in terms of the actual detailed properties of the galaxies. So you could imagine, for example, that
Oh, right.
if you're looking at the scale length of a disk, that can
Oh,
vary
yeah, no,
quite
that's
much
a very,
in
very
models.
good question. So I think, so that's a very interesting question, which we've been talking a bunch with people who do, let me answer the question in a different way. So when we do simulations for the large scale universe, we generate billions of galaxies at a time. And obviously we cannot get into the details of each galaxy. On the other hand, there are people who are doing very detailed individual galaxy simulations like the FIRE collaboration, and they do cosmological boxes, but within the box, they're focusing on generating only a few galaxies. So those galaxies have obviously all these details that you're talking about, disks and so on. So the interesting question is, and we've been talking with them, is over time, can their simulations become bigger and our simulations sort of go to higher resolution so we can handshake with them and come up with a new set of subgrid models that allow us to produce the kind of realism that you're talking about. My suspicion is this is not going to happen right away, but this is something that can happen on a decadal time scale. So I think it's definitely going to happen.
That's great, Salman. Thanks. So we do have a question in the Q&A tab. This one is from Emma Rath. Emma, thanks you for the fabulous overview. And our question is, at a high level, when simulations have been used to generate input to machine learning, will the machine learning simply learn what you already encoded in the simulation and not learn something new?
So this is actually a very interesting question of what exactly we term something new, right? So in some sense, what exactly is going on, and at the moment is, I mean, it's true that any database method, whatever AI-based method you have, is in some sense based only on the data that you give it. So it's not, so if you wanted to be able to do some extrapolation and go completely out of that data space, it's hard to argue how it would do that. No one knows. I mean, it's a hotly debated topic. The point I would make is that the advantage of running simulations is that you can run simulations in a way that you can generate data that isn't necessarily data that you can get from the real world. And it's also very controlled data. So you can say, you can have things in it that you couldn't get in the natural world, for example. So you might say, well, but this is synthetic. So in what sense is it better? So the answer is that it's synthetic, but it can have theories that aren't present in the natural world. And what might be happening is that the way an AI method might learn is that by giving it theories that aren't present in the natural world, we're expanding its horizons of what is possible. So in other words, we are assuming that there's some sort of universal space in which it can learn, and natural data only is a small subset of this universal space. But by giving it simulated data that has a bigger set of assumptions or a bigger set of parameters than the natural world has, you're allowing the AI method access to information that otherwise it wouldn't be able to get. So it's synthetic, but not in a space in which the natural world is. So that's the sense in which an AI model can become quite powerful if it's given extra information that otherwise you wouldn't be able to give it. I hope that makes sense.
We've got another question from Anon. How do you see how to build these composite software systems? That is, putting together modules for simulations, experimental data, instrument modeling, etc. Or is there already a solution for this?
Oh, there is no solution. So this is a very, very, very important point. So there's a massive amount of software engineering that has to go into this. So at the moment, I would say, I shouldn't say there is no solution. I would say that one of the things that we've learned from industry in AI/ML space is that this is something that, they have thrown so many people, and I should say so many smart people at this, that yes, there's a large software infrastructure that has been built in industrial space that we in the science domain can use. So I think what we can learn a lot from what has happened in industry and sort of build out our pipelines using tools that they have constructed. So the good news is that we don't necessarily have to build the tools. On the other hand, the kind of things that we do are often very different. So we have to modify them. But I think the software engineering task of how to put all these things together in a way that you can take them apart, put them together again, make something that is not fragile, is actually very, very important. But you can see already from all the nice work that's happening in current AI as applied to astronomy and astrophysics, if you look at any paper, you will see how seamlessly people are putting together lots of different software toolkits. So I would say that even though it's still a bit messy, the fact that you can put all these things together with teams of people of order 10 or smaller is actually very, very useful and important. So yeah, so I think this is a very important area. I mean, you want to have a situation where I, as a single person, can simply in one day, say, grab something from here, grab something from there, build a pipeline and get something out. And so I think AI/ML methods have a very strong kind of future in terms of democratization of science in a way that we can't do now. But yeah, I think it's very important.
That's great, Salman. Thanks. There are no other questions at the moment. I'd invite anybody in the audience to raise their hand if they've got a question for Salman. I'd also remind people that Salman will be one of the panel discussion members later on. So if you have any outstanding questions, you can raise it then. Okay, just waiting for. Okay, so it looks like we can wrap up there, Salman. So thanks very much for that talk. That was fantastic.
Yeah. No, thanks very much. Thanks everyone for listening.
Okay, so we'll see you later, Salman. So it's now time to introduce our second speaker, Ashley Villar. Ashley is an assistant professor of astronomy at Harvard University. She studies extragalactic transients, including supernovae, and develops statistical and deep learning methodologies for wide field surveys. Over to you, Ashley.
Great, thank you so much. I'm so excited to be here. Apologies, I will probably not be around for the panel because I will probably go to sleep. But you should be looking at my slideshow. I'm super excited to tell you a little bit about the research that my group is doing. So it's a fun complement and bridge between the talks, actually. So we study stars and the deaths of stars, which are called supernovae, but we don't do cosmology with those explosions. And I'll tell you a little bit more about why we care about stars that explode that don't just measure distances of our universe. And we do a lot of this, of course, with fun data-driven methodologies. Okay, and in particular tonight, I'm going to tell you a little bit about in this new era in which we just have a kind of an absurd amount of data available to us, we can start to ask questions of, well, is there something not in our physical bucket of knowledge that might be existing in the universe? And can we become sensitive to finding those new physical objects? And by that, I mean, we're looking for anomalies in the night sky. So first, let me tell you a little bit. My group does something called time domain astrophysics. And the way I like to describe this is to say that our universe evolves very, very slowly, as you probably know. So massive stars, for example, only live for millions of years. And to me as an astronomer, that's a very short amount of time. But of course, as a human, that's a very long amount of time. Time domain astrophysics really is the study of the universe on human timescales. So we're looking at the dynamic sky and how it changes on hours to weeks to months type of timescales. So what actually happens on those timescales? Actually a lot. One of our favorite things I've already mentioned are the deaths of stars themselves. In particular, I care a lot about how massive stars die. So this is kind of loops a little too much. So I'm going to go back for a second to talk about it. So these stars, I think there are astronomers in the audience, but for people who don't do astronomy, it turns out that stars live most of their life fusing elements into heavier and heavier elements. They kind of climb up the periodic table in this fusion process until we switch from an exothermic process that's producing heat to an endothermic process that unfortunately is eating up heat. So as a star, I'm continuously in this battle between gravity trying to pull me in, and luckily the exothermic processes of nuclear fusion that are pushing me out. When I turn into an endothermic process, then I end up actually collapsing in on myself, and I eventually bounce off for some interesting reasons, and I result in this interesting explosion. We see these explosions evolve on timescales that are dependent on the half-life of radioactive species that are formed in these explosions. And luckily, those are well-timed to human timescales. They can take weeks or months. And what's super fun about these, so supernovae, these explosions are so important for astronomy across the board. If you're not an astronomer, what I normally turn towards is to tell you that if you look at our periodic table and you color code it by the origin of these elements, very few elements are made in the beginning of the universe, the Big Bang itself. Really, that's hydrogen and helium. And basically everything else needs to be formed in the belly of a star. And the only way that I enrich the cosmos with that belly full is that I need to explode outwards. And so here I'm showing you that about half the periodic table, just above kind of the Iron Peak, is made either in the process of fusion of the star or during the explosion itself. I also just point out that the heavier I get, the more I need slightly more exotic forms of nucleosynthesis. And in particular, I end up needing really neutron-rich environments to make the very heavy elements. And we'll kind of touch upon that later on in the talk. So that's one reason why we really care about understanding these explosions. That's really a story of how these elements come to be, the elements that make up everything around us. It's not just that, though. Really, supernovae, especially massive stars, touch upon many areas of astrophysics. So one you've heard a lot about indirectly, cosmology. The explosions of white dwarf stars, a particular type, end up all looking pretty similar. So we call them standardizable or standard candles, which just means that because we know what the intrinsic luminosity or the wattage is, then we can really use them to measure distances. And that's how we famously use them to measure the expansion of the universe. But not just that, massive stars are also dominating the light we see from other galaxies. So if we want to understand those galaxies and how galaxies are generically formed in our universe, we really have to understand the stellar populations themselves, especially those of massive stars. So time domains, very fun, very important. Our group thinks a lot about the explosions themselves or eruptions, anything varying. And what I really love about the field of time domain astrophysics is that we get to explore such a fun, wide variety of high energy astrophysics that really does span an incredible dynamic scale in observational physics. So I'm showing you here a cartoon plot where I'm just showing how long something lasts very loosely versus how bright it is. Astronomers have this really goofy unit of measuring how bright something is called a magnitude, but just so you know, a more negative thing means it's brighter and it's on a logarithmic scale. What I really want to show you, though, is that when we look at the night sky, we see changes in the fluxes or the luminosity that we actually observe, and those changes can last for a very long time and be quite bright. In the case of having some physics that has a very rich reservoir of energy. So for example, if a supermassive black hole at the center of a galaxy far away from our own is actively accreting gas, I might be able to actually see a thermalization of that accretion in the form of what's called an active galactic nuclei. And that, like I said, that can last for like years and be incredibly bright. In contrast, I might have something like the merger of two super, super dense stars called neutron stars. And when they merge, they form these, actually, we mentioned this, these very heavy elements that are radioactive. And as those decay, I can see a very little, a somewhat dim and short-lived transient that we call a kilonova. So this is all to say this span exists in the universe and it's happening all the time around us. And we are, in a sense, just given those observations, and it's up to us to kind of put it on these plots. So that was a cartoon, but I really do want to emphasize that there's a sense in which this is the name of the game, that we have observables, that we see them in real time, and we attempt to organize them into their very disparate physical sources. In reality, these things heavily overlap in this kind of feature space I've made for you. A ton of these things, especially those supernovae, which are powered by radioactive materials, kind of all overlap with each other because they're all kind of driven by the same power source. So it's actually really hard to hand engineer these features to figure out how I can pluck out the different classes or types of physics available. This is a really, as all astrophysics is, it's a really old field. And so we have this incredibly, at this point, elaborate taxonomy and that we use to describe the physics that we see. I'm just going to give you a hint of this. Normally, to classify these transient objects, meaning they show up and disappear, they're transient phenomena, so like supernovae, we take a spectrum and then we just ask questions like, what elements am I able to see that are being excited in some way in that spectrum? And a really common one we have is like hydrogen. And that's an observable statement, but it really does connect back to the physics. So for example, if I see something that looks like the explosion of a star, if I see hydrogen, it means that that star has retained some hydrogen envelope, just like our own sun, although to be clear, more massive. And that's opposed to something where if I don't see hydrogen, but it's an explosion, then suddenly I can guess, whoa, somehow this star got stripped at some point. And so maybe that indicates that it's a white dwarf, like a type 1a, and I can use it to do cosmology. The more we find supernovae, though, I'll just kind of skip a slide, the more confusing this taxonomy gets. It really is this to me, very fun web of possible physics that's telling you the story of each individual star's life. And the way, what do I want to say? The features that we see in these explosions is kind of a combination of ingredients of what's actually the power source driving the explosion. Did the star have a buddy, like a binary companion throughout his life? And how did the star interact with its local environment? Did it kind of pollute it with material, or is it living in a clean environment? And all of this comes together to as a visual, what do I want to say, as a visual feature set that we see in the night sky. Okay, so our goal is to look at this kind of zoo and untangle the life story of these massive stars. So how do we actually do this? I keep saying like it's something that we visually see. It really is. So what we do is we have these wonderful robots that are attached to telescopes, and every night they look at patches of the sky and they look for differences or changes in the night sky. So here I'm showing you a picture of a spiral galaxy, and that wonderful green arrow tells us where the new star shows up, and that's a supernova happening in that galaxy. And what we do is we, in an automated ways, we find these new explosions, and then we kind of track them over time. And we make decisions in real time if we want to go get more observations to really understand that physics, or if we want to just let it move, if we want to move on, keep the data in our archives. I'm going to tell you slightly bit more about this. So I'm showing you a very similar picture here. I think it's just a simulation. Peter, who's on the call, will know that this is another kind of picture I'm showing you of the star itself. We don't use these pictures directly. Instead, we do one of two things. So the first thing we can do is to take a spectrum over time. And if we were to do that, we would see something like this GIF, where I'm showing you, it's a spectrum. I'm showing you the flux on the y-axis and the wavelength of those photons, or the color, in the x-axis, and time represents time. And so you can see there's a lot of really fun structure here temporally and in this kind of wavelength space that's telling us a ton about the makeup of the supernova itself, its energetics, and the progenitor star that led to this. In practice, this ends up being, we can't make these GIFs, they're really expensive. And so we end up making low resolution versions. So we basically just say, instead of getting every single wavelength, which is hard to do, I'm going to just look at, I'm going to group together all the blue photons and all the red photons. So I'm going to plot those over time. We call that a light curve. And that's what I'm showing here. So that's basically, imagine it's like the green area as a function in time. It still captures the physics, but it's a low fidelity kind of version of it. Okay, so that's the data we have in hand. And I want to emphasize that we have lots of this data, which is very fun. So supernovae have been pretty well studied for about a century now and like classified, and we've been trying to tell this story. Really only recently have we been finding them in a number that I would call big data. So here I'm showing you just a plot that's a histogram in log axis. As a function, let's see, how many supernovae are we discovering per year, starting in the 1980s, where we found like a dozen per year, which is pretty good. That's why I'm showing this light blue shaded plot. And you can see that discovery rate has been growing exponentially with time. And nowadays, we find about 10,000 of these events every single year, which is pretty cool. I do want to note that the taxonomy I showed you, that tree, is very much based on spectroscopy. So really getting a sense of all these little wiggles in the line. So we can say things like, do I or do I not have hydrogen? The gray line is showing you kind of the fraction that's actually getting one spectrum that we're using for classification. And you'll notice that that has also been increasing exponentially, but unfortunately, we're doing a lot worse now. So unfortunately, we only get about 10 to maybe 20% of all supernovae we discover get like a traditional label on them. And most of them just go to our archives. And to be honest, we don't do a ton of science with those right now. I will say that the game is going to change. I'll tell you why it's going to change in terms of numbers, but I'm not going to talk in this talk at all about the many fun problems of how do we classify things? How do you do like Bayesian hierarchical? How do you do population modeling with ones where it's all probabilistic? I'm not going to talk about that. I'm going to talk about kind of the fun, what happens when we find tons and tons of things, and how do you find the most fun events to follow up? Okay, so this is the state of the field right now, which is great. It's pretty data rich, although maybe if you're a true ML person, you might think that's not that much data, which is fair. What's really exciting is that very soon there's a new observatory that was mentioned that's going to come online. It's called the Vera C. Rubin Observatory that's actively being built in Chile and is a joint project between Chile and the United States through National Science Foundation. That is an incredibly large telescope that's going to begin a 10-year-long survey of the southern sky, where by survey, I mean it's taking like a really low cadence movie of the southern sky. So every few nights, it's going to take pictures in the same place, and we're going to be able to ask the question, do I see new stars showing up in that place? What's super cool about this is that because it's a wonderful mix of being incredibly sensitive that we get the deepest images we've ever gotten over the widest area we've ever gotten. It really is the entire southern sky into this just like truly unprecedented depth from the ground. So what's fun is that this is very much going to become a discovery machine and change the status quo of that plot I just showed you. So I'm waiting for a GIF I have to reset. Perfect. So I'm showing you the same plot, but now in this arrow, I'm showing you what happens in a few years when Vera Rubin comes online. And as you can see, it's very dramatic. It's partially dramatic because I made it linear scale, but I really want to emphasize like it really is super dramatic. So it's the same plot here, but you can see this arrow takes us up to an annual discovery rate of these explosions to 1 million per year, which is a break from exponential growth by about 2 orders of magnitude, which is so wild. It really is going to be this big data explosion that we're really excited about. I do want to point out that as this happens, there are some really wonderful efforts to help us also get follow-up. So to help us, when we find supernovae that we really want to study in real time before they go away forever, there are efforts to try to get those kind of spectroscopic resources. It's really hard to match the increase that LSST or the Vera Rubin Observatory is going to bring us. And so the fraction of events we can follow up in real time is going to drop from 10% to something like 1%. So it's really going to become a very selective field of what science is meaningful enough to be doing in real time with very scarce resources. And I'm going to spend a few slides just like emphasizing how important this problem is. We are in, I love to use the metaphor that there's a needle in a haystack problem. The haystack is the million of explosions we see per year from this observatory. And from that, I can only get a spectrum, so like one additional observation of, let's say, thousands per year, which is about right. And so even that's rough. But even from that, really the limiting resources is human power. We don't have that many astronomers. We don't have that many PhD candidates that can help us trigger the observations, write the papers, do the studies in real time. So I can optimistically guess, maybe our community will, in detail, follow up, understand, analyze 100 interesting supernovae per year. Math, 100 in a million, is roughly like saying about 1 in 10,000 supernovae can be studied in real time. So get any additional data on it. And what's kind of fun, scary, interesting, I don't know, about this is that that ratio is 1 in 10,000, or in other words, if we find 10,000 supernovae in 2024 this year, it's literally as if my entire community had a conference in which we decided which supernova of all of them we were all going to devote our time to this year. Like it's such a different way of thinking about this field, and what does it even mean to be important enough to follow in real time? Okay. So I'll say I have a super biased opinion because I don't do cosmology and I study the this kind of fun life and death of stars. And so I very much think that we should think a lot about the unknowns. We finally have a chance to find a 1 in a million or a 1 in 10,000 type of event. Very rare high energy astrophysics. And I think what's so exciting about this is that it really does mean that even for the most rare events, the things where we found one of them this year are suddenly going to become so commonplace that we shouldn't follow them up. Everything we know about now essentially isn't, this is controversial, but to me, might not be worth the resources of following them up because they're so commonplace. And we only get one shot with each of these explosions. So I think we really do need to prepare to ask the question, what's the unknown unknown that might be sitting in the data? And importantly, how do you become sensitive to that? How do I know, if I literally don't know what I'm looking for, how can I find it? Okay, I'm going to go on a tangent here that's a bit physics or astrophysics focused. So for astronomers in the call, I think this will speak more to you. You might be asking, like, why? Why do I care about these weirdos? Why do they matter? So the weirdos really do probe exotic high energy physics that is theorized but just impossible to be testing terrestrially, but still might have very strong implications on how our cosmos is evolving. So I'm just going to give one example of a theorized event that would be a 1 in 1 million type of observation. And this is where, gosh, all of my GIFs are kind of blinky, so I apologize for that. This is now going back to when I talked about the periodic table. I mentioned that those really heavy elements require really neutron-rich environments. I'm going to talk a little bit about why that is. And I'm setting you up for this by showing you a fun GIF of 2 neutron stars, which are very neutron-rich, hitting each other and forming these heavy elements. So the reason why these neutron-rich environments are so important is because to get to the heavy elements, we really need we need to have some form of a neutron capture process. In other words, I need to be sitting around as a seed nuclei, just meaning an atom with my neutrons and protons. And if I want to go up the periodic table, I need to be gaining protons, not just mass. But it turns out if I like throw a proton onto me, suddenly I have a charge and I don't really want to add more protons to myself. So one thing I could do instead is I could throw a bunch of neutrons on me. That gains mass, but until it beta decays, I can't actually turn that into a proton. That being said, though, I'm able to gain mass very quickly and to go up the periodic table if multiple of those kind of turn into protons. Okay, so that is to say that let's see, how do I want to say it? These neutron-rich environments allow something called the rapid neutron capture process to occur, in which I can, as a seed nuclei, gain many, many protons. They'll beta decay away, but then I've actually moved highly up the periodic table by gaining all of that mass. There are very few environments in which I can have such a neutron-rich arena that I can actually have the rapid neutron capture process occur. A really obvious one, theorists, is the collision of two neutron stars. And in fact, a few years ago now, in 2017, thanks to the gravitational wave detectors, LIGO, Virgo, we did detect gravitational waves from these merging neutron stars. And we pointed our telescopes and we were able to see the rapid decay of heavy elements that are consistent with models of rapid neutron capture process decay. So we know that at least one site, astrophysically, that can create heavy elements is the collision of neutron stars. There's lots of reasons astrophysically, though, to think that that's not the only site, and that there might be weirder, more exotic locations. This is a super confusing plot, and so I've just added labels for you. There's a really nice review about where do all the elements come from. That I took this from. But what I'm trying to show you here in this confusing plot is that when we look at stars in our Milky Way, we notice that, how do I want to phrase it? We notice that for some reason, there seems to be a lot of really heavy elements in stars that aren't old enough to be consistent with having neutron star mergers. Why is that? Because naively, neutron star mergers, so that is two neutron stars orbiting each other, the only way that they can come together is by losing energy in their orbit via gravitational waves. And that's like not an efficient process. And so it ends up just taking forever, basically. It takes billions of years for those things to actually lose enough energy to hit each other. And so we expect in general, there's a very big lead time between when I form the stars and when the things hit each other. So I don't expect really early stars to have these heavy elements, and yet we do see it. And so that's a confusing point if we think that all heavy elements are coming from these neutron stars hitting each other. Okay, so that kind of spurred some ideas of how else can you make this really quickly. One way you can make this quite quickly, and this is the exotic, have never been seen before, completely theorized to be clear, idea is that, well, maybe really massive stars in very specialized conditions, so if they form a black hole and it's spinning and has this accretion disk, it actually turns out that you can make an environment in which I actually do make heavy elements. And in fact, so working with, this is a while ago now, working with Daniel Siegel and Brian Metzger and Jenny Barnes, we theorized this model in which actually some of the earliest stars, which are incredibly massive, might actually form some of these heavy elements and can produce a ton of heavy elements, like up to 10 times the mass of our sun in these explosions. They'd be super, super, super rare, because one, if they weren't rare, we would have probably seen it by now. But two, also just the odds at which you have such a heavy mass star and it's spinning, its limitlessly, all that factored together means that it's probably a pretty rare population. But we actually did run the numbers, and we do predict that you'll find about one per year in the Vera Rubin Observatory's survey, that 10-year-long survey. And so this is a good example of if you found this, what a fun smoking gun signature that really solves this question of astrophysics right now. Why in the world do we have quickly forming heavy elements? But it is something that is such a weirdo. It's such an anomaly, and it's definitely incredibly rare to find. Okay, so that was a fun physics aside, mainly for entertainment, to tell you that there is reason to really care about these weirdos. Now I'm going to shift gears and talk a lot about, at a really high level though, the ML techniques that we're using to try to find these anomalies. First, I'm going to tell you what is an anomaly to me. And there's two anomalies that I think about, but there's only one that we're really sensitive to right now. So the one that we're sensitive to is probably the one that you think of and that I think of when we say anomaly, and that's an out of distribution anomaly. So here I'm showing you, let's get this great graphic of, pretend I see lots of supernovae on the sky. I see their light over time, and I have physical models where I can fit those physical models and infer properties of that explosion. In particular, I'm pretending that I can infer the energy of the explosion and the mass of the star that exploded. And here I'm just showing you, pretend I only know of two different types of stars that can explode, like white dwarfs and what are called red supergiants. It doesn't, none of this matters. It's just two types of stars, two types of explosions. I put it on a plot. Out of distribution anomalies are anomalies like this cow, and there's a reason I chose a cow, but I'm not going to tell you, where what we're really asking is, in this latent, or this unseen parameter space, so I don't directly see energy, my eyes can't see, I don't know, they kind of can, they can see wavelength, but they can't see energy of the explosion. I have to infer that. So it's unseen to us. It's not like a feature I observe. It's actually a latent feature that I infer. So in this latent space, I've seen many supernovae, and I've seen enough where I can actually have a density estimate, and I can say, oh yeah, I definitely see a lot here and here. And out of distribution anomalies are ones where I say, I'm in a really low density region. Very few things seem to happen here, like this cow. And the way that my field has primarily looked for these things is actually super easy. So we make these kind of latent spaces, and then we just ask the question, who amongst these points is in a low density region? So to do that, I use something called and we all do in the field, we use something called an isolation forest. That's pretty easy to understand. I take my latent space, I make a random cut in one of the features, like energy, and I just say, I'm going to make a cut here. And then I subdivide the space into the left side and the right-hand side. I make a second cut, let's just say here, but only in one of these dimensions, and now I have kind of these three sectors. I keep making cuts, blah, blah, blah. And as I keep making cuts, I can ask questions like, hey, how many cuts did it take to put this cow in its own space versus how many cuts does it take to put, oh gosh, I don't even have one, this guy in his own space. For this guy, it took many, many cuts to get him in his own space. And for the cow, it took very few cuts to make him in his own space. So in a sense, the number of cuts it takes, or the number of branching decision trees I need, inversely tells me about how weird I must be. If I don't take a lot of cuts to isolate me, I'm probably pretty weird. But if I take many, many, many cuts like I do here, I'm probably sitting smack dab in the middle of my distribution. I'm probably not very weird at all. So that's how we find these anomalies. I just want to point out briefly, and I don't have a slide, okay, about the physics of this. I want to point out that there are other types of anomalies. The only other one I want to mention is this idea of a contextual anomaly, where maybe I'm in this like red regime, but suddenly I see something that I thought should look red, but it looks like this catfish instead. And the idea there is, well, in the context, I expect X, but I actually see Y happen. And this is also very interesting physically. I just want to be clear about that. But everything I'm talking about is not sensitive to those types of anomalies because they're in high density regions. It's in this particular latent space, and so I can't select them. But it's a very fun problem to think about. Okay. So in this description, I talked about this latent space that was very physically informed. I said one dimension I'm going to call energy, and one dimension I'm going to call mass of the star that exploded. And to get those, I'm going to fit lots of models to my explosions. I will say it's actually not trivial to generate that space. And in fact, it's not possible to generate that space. Why is that? Because, as I mentioned earlier, the cosmos is a zoo of high energy phenomena. Some of these events that I meant, even the ones I mentioned, like the supermassive black hole eating gas onto it, what is the mass of the star? It's a black hole. It doesn't make any sense. What's the energy? It doesn't make any sense. There is no one model that I can just write down to describe all physics I see. It's not possible. And the diversity I see is in some way, almost by definition with anomalies, I can't know it a priori. And so because of this, we more often than not turn to a very physics agnostic version of these same plots, where we build up our latent spaces using fully data-driven methodologies. And these were kind of mentioned before, and I'll just talk a little bit about autoencoders. But the idea is that I have these time series, and I just want to find a latent space, so some vector space, where I can embed these physical data streams into to help me still make these types of plots and to do this type of analysis like an isolation forest. But I need to make it physics agnostic because I don't have a model that I can use. Okay. So I'll just say that one of the ways that we've been doing this in at least my group is we think a lot about autoencoders. What do I want to say? I think this group knows a lot about machine learning, so I probably don't need to talk too much about this. I think what I just want to maybe say in a jargony way is that what's fun to me about my field is that, and I've really glanced over a lot of this, is that we have interesting multivariate time series that tend to be sparse and irregularly sampled, that we need to coherently encode into fixed dimensional latent spaces. And so because of that, we typically turn towards these autoencoders where we can explicitly encode things like the time lag between observations and in what filter or in what wavelength we actually observe the photons in. Oh yeah, okay, I guess I didn't do this. I'll also just mention that for this anomaly detection work, we also typically use just kind of a vanilla, but a variational form of this, so a variational autoencoder. So you know, I think that variational autoencoders don't just build up a latent space, you also get kind of an uncertainty on top of that. But more importantly, and I'll show why this matters, is that we get some regularization on the space to make it continuous to help us with our density estimates. Okay, so I think I said this already, I forget. So right, because we have data coming in real time every night, we do try to, we build these in a recurrent way where we can update the encoded vectors, so how we're embedding each light curve, or the data that we see in real time. I just like to show this series of slides that shows you an example, and in case you don't know how autoencoders work, it doesn't really matter. The key point here is that, so what we do is we have some method, this neural network, that looks at data we observed. That's why I'm showing you in these points. So the point represents the observation, and this error bar is the uncertainty. And again, remember this weird unit, this is just representing how bright something is, where this is brighter at the top and it's dimmer at the bottom versus time. Okay, so those are the points. And then the lines are showing you what this autoencoder predicts the light curve, the data should look like, so the explosion should look like as a function in time. And what's interesting is that with very little data, we are able to make predictions that seem consistent with what we expect physically for these type of explosions. So it hits roughly the right magnitude. I'll just go ahead. And And so without even specifying the physical model, we get something that looks roughly right. And I'll say, you know, it's pretty old. At this point, we do much better than what I did a few years ago. So that's great. The reason why we do this is because we're able to build these models by just showing in a totally unsupervised way this autoencoder many explosions from the night sky, and it's able to build up a representation of these supernovae and reproduce the data, and importantly, build up that latent space so that we can start to ask, where are the interesting anomalies? So we can take many supernovae, which is what I'm showing you in this scatter plot. We can encode all of them into these somewhat, you know, not meaningful features. They're not, this isn't a physically, I want to be very clear, we're not interpreting this as anything, but we can build up these latent spaces. And because we've used this nice vanilla variational autoencoder, as we know, our KL divergence with the normal distribution encourages it to be centered on 0 with a standard deviation of 1. And that makes a nice continuous density distribution. And we can ask simple questions like, hey, which of these points are in a low density region? And that's what I've marked in purple. And so what's fun about this is that I can try to find these interesting anomalies in real time. So we did this a bit ago now with a big simulation of the Vera Rubin Observatory. So there was this like really wonderful community effort that I always love to highlight called Plastic. It was a Kaggle competition run by like Renee Holtchek, Rick Kessler, and Gautam Narayan, amongst many others, that said, let's come together, put all of our physical models together and try to simulate the night sky, and then take a guess on what it's going to look like. So of course we can't simulate unknown physics, but what we're able to show here, at least, is that for this autoencoder-based method, we do in fact flag, I mean, I guess you're gonna have to take my word for it, there's a lot to take in at once. We do flag in general the minority classes, so the more rare physics, as being more anomalous, which is really exciting. And I think one thing that's very fun is that we can look at the very rare types of supernovae in the simulation. So here I'm showing you one, it's called superluminous. I don't have to describe the physics. And we can watch as a function of time that weirdness score from the isolation forest evolving. And we can ask a question, at what time in its evolution, so at each time point we re-embed it into the space, we can ask at what point does that weirdness score start to become the highest percentile? I don't forget, honestly, if this is like 1%, 0.1%, I just don't remember. And you could imagine that we would have triggered our telescope. And what's so fun is that in this case, we would have triggered our telescope very early, which means we would have gotten a really nice data set to really understand this type of event. And what's happening in time is that, so in black, I'm showing you just the full sample of supernovae. These purple points all represent this one weirdo, but the darker color, let's see, the coloring of these dots gets darker with time. So in other words, you actually kind of watch it walk away from the distribution as it becomes weirder and weirder according to this isolation forest score. So the embedding really does, as I become less prior dominated and I have more data available, I can kind of see me move away. So that's super fun. So let's see, what do I want to say about this? This has been really exciting. It means that there is a path forward using pretty standard ML techniques that are in many ways physics agnostic to find new physics. We have kept working on that since then, so I'll tell you a little tiny bit about what we've been doing. Most recently, through something called the Young Supernova Experiment, which is another survey of the northern sky, actually, that's happening right now. We have been building active anomaly detection algorithms that are running on real data, not simulations. And in particular, so this is really great work by Patrick Aleo, who just graduated from UIUC. What we do is we take our data, the explosions we see in the night sky in real time, and we also take the picture of the galaxy they exploded in. And we put both of those pieces of information, so the image and the time series, into the same joint embedding space. And then in that embedding space, we actually ask like a few tasks from that. We do things like we ask for, well, we're not doing classification right now, but we ask for nearest neighbors, which I'll show you in a bit. And we also do ask for things like, what is sitting in a low density region? What's an anomaly right now that we can find in real time? So what do we actually find? So apologies, like it's hard to describe all the physics at once, so I'll just say a few things about it. Let's see. This one, unless you're an expert on supernova science, it's not going to look weird to you, but it is weird. So here's a fun event that came from what's called the Zwicky Transient Facility. That is just an ongoing northern survey that's looking at the night sky. This supernova is weird for a reason I'll describe in 1 second. It's called a type 1b. That just means that this is a massive star that has, for some reason, lost its, so massive stars are like onions, and they get heavier and heavier elements with each inner layer. This star has lost its hydrogen envelope, but it still has retained some of the helium right under that. So it's got like its little second onion layer still. That's not so weird. These things are kind of rare, but not incredibly rare. But what's so fun about this one, though, is that it has this incredibly asymmetric shape that's very unusual for these types of supernovae. So what's fun is that this was noted as incredibly anomalous pretty early on, and we were also able to get a spectrum early on, although had we had this running, we would have been able to trigger much earlier and really understand what's driving this early emission that we see in this supernova. Because we do this kind of joint embedding space, we can also ask for contextual anomalies, meaning looking at the environment the supernova is living in. Is that something that looks strange? And here I'm just showing you some fun examples. I tried my very best to turn up the contrast on these, but these are fun because these are pictures of the galaxies that these interesting supernovae lived within. And these are both these halo galaxies. So you can kind of see here, there's this weird blue ring. And you can barely see this. There's a blue ring here too. So these are very strange. They're probably from mergers, and these are these rings of intense star formation and massive stars. And these supernovae are occurring in these. And so these stick out because it's not that the supernova looks strange, but the environment it occurred in was incredibly odd looking. Okay, and so I will say in real time, the way this works, which is quite fun. So anyone can access this data. It's living online right now through something called the Antares broker. But we, as a collaboration, this young supernova collaboration, actually every day, like 9 a.m., it's very fun when I sit down with my coffee, we get a Slack bot alert that tells us about the most anomalous candidates that we have. And it has an active feedback loop that we're not using yet, but we're hoping to use soon, where we actually do kind of, you can see at the bottom here, we upvote whether or not we think it's anomalous, or if we think it's this other, we're not so interested in these things called HENs. We also kind of make notes if it's that. So we do have these kind of bots that aggregate the information, they actively filter out these anomalies, and then send us the top 3 candidates every day. I also just want to mention in passing what's so fun about these kind of embedding what's fun about doing representation learning that builds up these latent spaces is that you can ask questions of the latent space that are hard to formalize otherwise. So by that I mean you can do things like a nearest neighbor search. So one thing you can do in this LACE methodology is that you can say, hey, I have an event that looks like this. Sorry, this is a little hard to see, but in this plot, which is the light from the supernova as a function in time, you can see these bright red points as opposed to these dim red points, and these bright green versus these like low opacity green. These bright red and the bright green are from one supernova, this guy, who also came from this galaxy. Everything else is actually the nearest neighbor from it. And so we look for events that have both similar homes that they're from, the galaxies themselves, and light curves. And so I think what's really exciting is that in the era of something like Vera Rubin, when we find these really anomalous guys, we can ask questions like, okay, you might be in a low density region, but who is your nearest neighbor? Is there a class that can emerge from these kind of very sparse areas? And then I'll just say one more thing, which was mentioned. Foundation models are definitely all the rage. And it's also very much all the rage in time domain astrophysics. So we are really thinking a lot about these representation spaces that are multimodal, that use these images, that use these time series, and that use spectroscopy all together. And one way I've been thinking about this a lot is thinking about this multi-view, this multimodal view of the data as kind of your back end to how we talk to data, how we mind map and organize it. And in the front end, we're pairing this with large language models. So apologies, it's a little bit blurry, but we pair it with large language models via chatbots where we can actually ask questions via SQL queries of the database we have. And we can pair that with RAG to actually give it some astrophysical context of the physics we might be interested in. So I really want to highlight that this work is done by a really wonderful postdoc, Alex Gagliano, who's an I5 fellow, joint between MIT and Harvard with my group, who has been working on this fun chatbot called the Speakeasy for the Young Supernova experiment. Okay, so I'm going to end there and just say that I hope I've excited you a little bit about finding these really fun anomalies in our kind of cosmic haystacks. And I want to just, if it's okay, end to say that in my intro, I think it was mentioned that I'm part of a science collaboration called the LSST, Informatics and Statistics Science Collaboration. If you are interested at all in some of this work, you are welcome to join. Anyone who's in data science or astrophysics is able to become a member and work on some of these fun problems with our astrophysical data. So I'll end there and take questions. Thanks.
That's great, Ashley. Thank you. That was a really, really cool talk. We don't have any questions in the Q&A yet. I'd invite people to enter their questions and we can ask Ashley. I'd also invite people to raise their hands if they want to ask a specific question. While we wait for that, Ashley, one of the things that came out from the talk was how this data-driven approach allows you to identify features in latent parameter space. So it looks like that theory may need to play a bit of catch-up here. How exactly do you foresee the theoretical interpretation interacting with the approach that you're taking so far?
Yeah, that's fair. You're totally right. I actually see them as running in parallel. So there's this kind of there's the broader question of how do stars live and die and what's driving their explosions. That has to be paired with traditional statistics. Like it just has to be. But there is a sense, this was mentioned, uncertainty quantification from these ML methodologies is so necessary to answer that. And that's something that we're very actively working on. And it's challenging because there is systematic uncertainty where the theory truly does not match the physics we see. Explosions are really complicated. That's kind of aside from just finding the cool things that we really don't know about. And there's kind of an expectation that, of course, we don't have the theory, but we're hoping first and foremost to get all the data we can get so that we can build models around that data.
Okay. Any questions from the audience for Ashley? Okay, well, if not, oh, okay, great. So Fatima Hafezian, thank you for your talk, Ashley. It was great and interesting. What was the name of the group that we can collaborate related to Astro and ML? Yeah, I can see you're answering now. So I guess that's the LSST group.
I'm typing it just so it's really clear. Yeah, so that is the LSST. Did it work? No.
Oh, the cow.
I can't explain.
From Lorenzo Campoli.
Yeah. So I will just say that yeah, everyone's welcome to join that group. It's, again, very much open to professional data scientists or astronomers, and it's very fun to play with Astro data, in my opinion. It's very fun if you're interested on open source software or problems. The cow is kind of goofy, so it is a funny story. So the way we actually name our supernovae, but we name them just based on the year and then alphabetical count up. So we start with 2024 A and then B, blah, blah, blah. So we find so many that we get to like several letters. And so I will note that it gets kind of goofy a lot. And so very famously, there is this one event called 2018 COW, or the cow, that really was this oddball anomaly that we still don't know what the origin was. It was very, very fast and very bright, which is actually where the cow was sitting in my little feature space. But that's where the name comes from. It just happened to be COW.
Thanks for clearing that up, Ashley.
Yeah.
Okay, are there any other questions from the audience? Okay, well, if not, I'd like to thank you again, Ashley. Oh, one more just now. Is the large language model continually being updated?
Yeah, that's a really good question. So yes, I think everyone who's Yuan-Sen, actually, maybe I shouldn't speak for you. I assume Yuan-Sen's going to talk a little bit about LLMs. He does a lot of work with them. Yeah, we update them as new open source models come out, which, as probably everyone here knows, is like roughly every 6 months, if not faster, and it's kind of wild. So yeah, we do update that way. We don't do active learning though, as in we don't actively fine-tune with the users. We just use the context windows that are typical in these large language models.
Hi, EPNV. Thanks you for the talk, Ashley. Why VAE, an autoencoder or a PCA could be okay?
Yeah, the autoencoder. So actually, I'll start with PCA. The reason why PCA is not the most obvious thing to do, and this isn't, so this is actually a place where it helps to know a little bit about the physics. So as I tune up linearly a physical parameter like mass, I expect to stretch out my data in a nonlinear way. So I very naturally expect that there must be some kind of nonlinear space I want to embed into. Okay, so that's a reason to not choose PCA. And then autoencoders are totally fine if you want to do things like classification. In this particular case, we really wanted to do anomaly detection. So we really actually wanted this continuous dense distribution, which is why we chose a variational autoencoder.
Okay, thanks for that. Any more questions? People can also raise their hand if they want to ask Ashley directly. Okay. I'm not hearing anything else. So thanks, Ashley. We'll let you get to bed. I know it's pretty late there.
Yeah, thanks so much.
So
yeah,
Chris,
thanks for that. That was
Chris,
fantastic.
there's a question. So Chris, Eric Miller has a question.
Oh, okay, sure. Eric, do you want to speak?
Sorry, yes, I think it's just unmuted me now. Sorry, that was actually a misclick on my end. Apologies.
That's okay, no problem.
Thanks anyway for the great talk.
Okay, thanks, Eric. Okay, well, I guess, yeah, with that, we can say goodbye, Ashley. Yeah, have a good sleep, and yeah, thanks for the great talk. Okay. So now it's time for me to introduce our third speaker, Yuan-Sen Ting. Yuan-Sen holds an associate professor appointment at both the Australian National University and also Ohio State University. His work is at the nexus of machine learning and large astronomical surveys, extending Bayesian statistics with deep learning methodologies. So over to you, Yuan-Sen.
Okay, thank you very much. Let me share my screen and do the full screen. I presume you can see my screen?
Yes.
Okay, great. Okay, and thank you, Chris, and good morning, everybody. I really love to give a remote talk because I can wear my jacket and Lululemon at the same time. But anyway, so as Ashley say, I will be mostly focusing on large language models. So actually did end at a good point. I will just continue to talk about what I think about large language models and why I think it's quite a game changer of how we do astronomy. So let me start by talking about why we are all here. So obviously there are lots of interest in AI for science. So for example, in the US, the NSF has awarded about $200 million for AI research, and half of them is actually dedicated for science, right? So if you count the biological sciences, the physical sciences, and the environmental sciences. The question that, of course, we are all here to discuss is whether or not this is a hype, a myth, or a real deal. And so, of course, there's reason why people are so excited about AI for science. I think a big part of that play a big role is the AlphaFold, right? So people say since the AlphaFold has totally transformed how we do life sciences, we should expect to see that for the other field of sciences. And because of that, right, so quite often I got asked the question from non-astronomer and in AI about why there is no AlphaFold a moment yet in astronomy. So of course we have, I didn't plan for this, but of course we have heard from the first talk that like a lot of the effort in AI for science are focusing on two regimes, right? So on the one hand, we are extending how we do statistics, and including I myself has been working on that, in particular in cosmology, and try to understand the state of the universe. And the other regime is what Ashley talked about, because there are more and more data that are coming online. So of course you need a very efficient broker or classifier to find the anomalies. And all of these are super important, and I have been working on that. But I would argue that none of this is really at the level of the AlphaFold, right? So this will improve how we do science, but it would not fundamentally change astronomy, not at the level that the humans still need to be involved. And the thing that I want to talk about today, I will start by this famous article called The Bitter Lessons from Rich Sutton. So what Rich Sutton mentioned is that in the regime where we have a system that can scale up to arbitrary complexity, the right way to think about the question is try to understand how we can let the agent to discover like we can, instead of we instructing them to discover as we want. So I think this is a important part that we need to distinguish, because a lot of things that we have been doing in AI for astronomy has been focusing as you're using AI as the tool. So we are instructing how the AI should do the discover as we want it to be, instead of letting the AI to help us, to instruct us to do science. So with that, so these are the three things that I want to discuss with you today. So one is where we are at in AI for astronomy. How do we quantify that? What is the problem? So I think I mentioned a little bit of the problem in the last few minutes. And I want to talk about what I feel could be a AlphaFold moment for astronomy, right? So I still think a lot of things that we're doing are amazing, but we also need to have some blue sky research that will change how we do science. And of course, I will talk about how we can get them more efficiently. So let's talk about where we are at in terms of AI for astronomy. And in particular, how do we sense the growth of AI for astronomy? So there is a lot of interest in AI for astronomy, but how do we quantify that? How do we know if AI is really helping us to do science? And how do we understand that interaction? So this is a thing that I got quite excited about in the last few months, mainly to understand the knowledge graph in astronomy. So what is showing you here is a knowledge graph that we constructed with Microsoft. So what we try to do here is try to go through all the literature in astronomy and try to understand what are the concepts that appear in astronomy. So in this case, this knowledge graph has about 25,000 concepts, and we try to understand how these concepts interact with each other, and from which we can start to understand how to quantify the influence of AI. So of course, I will tell you how we get there, so that just to show you the knowledge graph first. But let's talk about how do we really quantify that, right? So how do we construct the knowledge graph? The first thing that we do, of course, is try to expand how we visualize the field, right? So like a lot of things that we have been doing in astronomy, quite often we are relying on keywords. So if you write a paper, you have to select the keywords from these 1,400 words that we call UAT, the Unified Astronomy Thesaurus. But A, like that is too limiting, it's too granular. But B is also like a bit like outdated, right? So if you, in order to keep up to date, like what would be the new concept to appear, it's very hard to do that with the UAT, because that has been set even you get like updated every few years, it's still too late. So what we end up doing is to use large language models to extract all the concepts in the paper. So no one can read all the paper, but large language models can. So this is nice. So let's start by talking about the basic thing, right? So let's see how the concept has changed over time. So how much the concept has grown over time. So what is showing you here are the number of concepts in thousands as a function of years. So if you're just focusing on the concepts that are related to science, then it grow from about 7,000 to about 11,000. So that's quite healthy. So the number of concepts in the last 50 years have grown by like 50%. You can also look at the concepts that are related to a numerical simulation. So Salman talk about that, as well as the statistic. And this is also quite healthy, right? So the number of concepts that are related to the simulations grow from about 1,000 to about 1,500. But the same cannot be said for machine learning, right? So if you just count in the literature how many of concept has new concept has appeared, it has grown from like 150 to about 230. And this point to a problem, meaning that there is a lot of hype about like applying like machine learning to astronomy, but a lot of things that we are doing, of course, are still relying on somewhat older methods. But we can also like further like quantify, right? So also as I mentioned earlier, the goal here is try to understand how these different type of concepts are interacting with each other and how they inspire the growth of science. And this is something that we try to quantify like better. So in particular, we try to understand the distances between the concepts as a function of years. But how do you understand the distances of concepts? So what we did here is try to use a literature citation metric, just try to understand how the community is viewing the different concepts. So let's say I want to understand the concepts between dark matter and plasmon. What I would do is to find the paper that contain the concepts dark matter. I will look up for all the papers that either cite this particular paper or reference this paper. So you can count the number of paper that this paper cite that contain the other concepts. So this, of course, is a one distance, meaning that if I want to understand plasmon by already knowing dark matter, I just need to read two papers, right? So I need to read, like this paper in red. But if I also read the paper that cite this paper, I will lead to the other concepts. But you can imagine there are many concepts that are further away, so you cannot directly reach them with one distance. So if you grow the sphere, then the number, the denominator will grow. So how we define the distances between the concepts here are just saying that like in terms of probability, how likely you will encounter a new concept B by reading all the papers that is related to A. But there's just the technicality, but like with that, you can start to see how these two different type of concepts are interacting with each other. So what is showing you here, the y-axis are the average distances between the concepts that are from the numerical simulation with the concept that are from science. And for this technical and scientific interaction, you often see this two-phase evolution. So what are we seeing here? So let's focus on this phase, right? So if you look at this phase, you will see the concepts that are related to the numerical simulation are decoupling from science. And this is what we call the technology development. So the way to think about this is that like around 2000 to 2005, there are lots of people who are developing n-body solvers. So they are interested in the technology. So they are developing quite a lot of new techniques, but they are not necessarily applying that to science, right? So, and this is why you see the linkage decouple. But after a 5-year like evolution, then people will start to deploy the new techniques, meaning that now people are using the concepts that has been developed in a numerical simulation and try to run n-body simulation. Right? So this is why the linkage increases. And similarly, you can see the next 5 years, if people are familiar with the evolution of the numerical simulation, this is also the time where the hydrodynamic simulation are becoming more and more popular. There are more technologies that are bringing in these new techniques. And then this leads to like another boom of sciences. This is very healthy, right? You have this two-phase evolution. The way for astronomers, like the way that you can think about this is like dwarf galaxy star formation. So you accrete some gas, and then you have, and this leads to starburst, and then you accrete more gas, and then this leads to a starburst. But the same thing is not the same for machine learning for science, and this is somewhat concerning because you can see that there are lots of interest in machine learning and astronomy, but there are really not many accretion of new techniques. And I do see that to be a problem because this meaning that like a lot of these cross citation that we see are still like relying on older like techniques that has been brought in like around 2010 to 2015. And of course, the problem here is that machine learning is a very fast-paced field. So if you are not like actively accreting more and more new ideas, then they would drive out the technologies in astronomy. So that's one of the way to think about like astronomy and AI. I think there are lots of like interest, which is great, but also see there are some problems because we quite often are not like distinguishing people who are applying the technique to science, which is great, but also to reward like people who think about the technology, right? But there's also a bigger problem than just the slow accretion of new techniques. And this leads to the question that I posted, that I was like posted like many times, which is, where is the AlphaFold thing, right? So what is the one thing that the AI will change astronomy? And I think that question like itself is quite posted because astronomy is not a biology. What do I mean by that? So if you think about for most of the analysis that we try to do, it often goes as I have some data and I want to test a theory, right? And then we analyze the data to decide if the theory is true or false. And for biology, like this is particularly like important because in the past, when you have no way to predict the folding of the proteins, then you do not have a way, even for that one task, like you have no way to prove or disprove your theory. And this is why when AlphaFold happens, it gives you a pipeline, which leads to a breakthrough, right? Because for this particular like downstream task, biology is a bottleneck by this one task. But for astronomy, like this is quite different because like astronomers are smart. So we kind of know a lot of things already, right? So like that's just a joke, like meaning that, you know, like astronomy, like in many ways is a simpler than a biology. So in a vast field that we already have a pretty successful pipeline. It's not like we cannot do without, right? So this is why if you think about the application of AI to astronomy, quite often, say in cosmology, it would improve 10 to 20%, but it will not change drastically. It's not as drastic as AlphaFold. So it's not that it's not important, it's just that it will not have the impact. So if you're asking an AlphaFold a moment to convince the senator, I think like most of the things that we are doing are not at that scale, and it will not lead to that scale that we have this like a blue sky type of research. So what could be a AlphaFold moment for astronomy? And this is the thing that I've been thinking quite a little bit, as Ashley mentioned. One of the excitement here is building toward a AI astronomer, meaning that we try to automate the research completely. But let me dissect a little bit, right? So how should you think about this question? So if we have like established that individual downstream tasks is not a bottleneck, then you should take a step back and talk about what the human is doing now. So in astronomy, like most of the time, we are not bottlenecked by a single task, but the role of the human quite often is try to evaluate the state of the research, right? Meaning that, say, for example, a supervisor will look at the PhD student and decide, if the this direction is good or bad, and like propose new theory or new data. Like new data meaning that you can like propose a new telescope, new wavelength, and a new way to collect the data. So humans are often taking the role of an outsider, right? So we evaluate the state of the research and propose the new action. And in a way, that this is very, very similar to playing Go chess. So one way to think about like research is that we are essentially doing a reinforcement learning. We are playing a chess game, like just that the chess game is the research. So by playing more and more like chess game, a more experienced researcher will get more experience and know how to propose by evaluating the states and know how to propose a new theory. So perhaps one way to think about how we can automate the research is to do the reinforcement learning. But there is a problem here, because what we call the state of the research is more fuzzy than a chessboard, right? So the human can understand, a very experienced researcher can understand the state of the research, but this is not that trivial for and this is not something that we can like define this as a mathematical reward, because this is all quite implicit, and this leads to a lot of bad taste about AI. Like if people don't understand like AI, people always say, well, like even with AI, we are still relying, like at least for astronomy, we are still relying on the human intuition or experience, like what Ashley talk about, like using the human to upward or downwards stuff, because those come from years of experience and it's hard to mathematically quantify that. The question is, can we actually do that, right? Can we mathematically quantify the intuition? The answer is yes. So you can still do this type of reinforcement or learning, like a policy learning without a reward or function. And the trick here is using the LLM as the rewards. So the LLM, the large language models, implicitly have some intelligence, and hopefully those LLM is strong enough that you can use them as a reward function. So this of course sounds like a bit meta and high level. Let's talk about a specific case that we thought about and we have written about. So let's talk about this simple case where you are feeding a SED of a galaxy. So the SED stands for the spectral energy distribution. So you're looking at the flux of the galaxy at a different wavelength. So the data point here are the data point from James Webb. So let's say you collect some data from James Webb and you feed a physical models, right? So you have some baseline models. You ask your grad student to fit that. And then your grad student will run to you and say, hey, I fit the base models, but I see some discrepancy. So let's talk about what a human would do here. So if you are a experienced researcher, what you would say is that, hey, maybe you should see that the discrepancy have a wavelength dependency, meaning that it's estimated in the optical, overestimated in the infrared. So this might mean that maybe your dust models are wrong. So you should swap out the dust models in your physical models. The other hypothesis will be, well, you are estimating the ultraviolet flux. And we also know that young stellar population can create the ultraviolet flux. So what could be wrong could be your models are wrong. This is why you need to swap out, find another GitHub that have a different parameterization. And even with this simple example, you can start to see some of the problems, right? Which is lots of things that the human do are not mathematically differentiable. And it's not only optimizing the chi-square of the fit. Lots of this is human intuition and human experience. The question is, can LLM learn through experience, right? And that's the question that we try to pose. So we have this program that we call Mephisto. Why is a Mephisto? Because Mephisto is this a demon that exchanges soul for knowledge, right? So the same thing here, we are exchanging our soul to the AI overlord and try to exchange for knowledge. So how does that work, right? So essentially it's what we call the agentic research. So we are using a collaboration of different agents and see how well you can do the science. So in particular, in this case, we have different agents. This is, of course, a very romanticized way to look at things. In practice, this is what happened. You have many copies of Mr. Smith, and they are all like GPT-4, right? So you try to say, can I really use like GPT-4 and give very specific tasks to different copy of a GPT-4 with fine-tuning, with a retrieval augmented generation, so that you can do the science and learn from the exploration. So in particular, we are using a particular case that we use the data from James Webb, which is quite exciting because people have been looking for a high redshift galaxy from James Webb, the earliest galaxy that we can find. You can also define, you also need to define a playground. So we ended up like defining the playground using this code called Seagull. But Seagull is not just one code, right? So Seagull is a collection of codes that with different physical models, meaning that you have different building blocks, and the LLM need to learn how to play with the building blocks. So this become a very concrete chess game. And the closest analog that you should think about, keep referring to, is essentially alpha 0. So let them to play the games, and hopefully by playing enough games, you will learn how to play the chess well. So just that now the chess become feeding the SED. So how does that work? So as I mentioned, you can start with a baseline feed. You have some data, you have some baseline feed, like this is your current state of the chessboard. And then Mr. Smith, number 1, will comes in, and this particular agent is tasked to propose action, meaning that this board has all this information like what actually has for a chatbot. So you have a lot of contact-based information, and it's very good at proposing actions. So you propose a bunch of actions, so let's say 1, 2, 3, 4, and then you have another agents, Mr. Smith number 1, and what Mr. Smith is tasked to do is to write the codes, right? So it will use, based on what has been proposed by the action, it will write the configuration file, run the codes. So if the codes do not run, then it would debug the codes. So you write the codes, and then you would generate new fits. And then you have the other two agents. One is to look at the plot, right? So you have these two new results, just like you play the chess, you play 2 different moves. And then you have this board that will learn how to summarize the experience. So this is state evaluation. But this is also quite implicit. It's more than just optimizing the chi-square. You are using the LLM as a agent, and hopefully it can understand why something is better than the other without really relying on a single error metric. Of course, all the LLM are limited by the context of Windows, so you have like another like agent that do the distillation. So after you have done that, it will store your knowledge, right? So this is more than just prompting the LLM, because you are really let the LLM to explore the data and store the knowledge. So how does the knowledge looks like? So this is one of the example of the learn knowledge. So after by playing the games, so the LLM will learn that now if the fit is over estimated in UV or optical, I have learned that maybe changing this particular parameter, EB minus V, which is the parameter of the dust, it might help to improve the models. So this is the type of knowledge that is not implicit to say like GPT-4, because you would not know how to run the CGL code implicitly, but letting them using them as an agent to interact with the real world like data, you will start to summarize some of the knowledge. And does that work, right? So this is of course still very like conceptual. And actually it works. So what we have shown here, that we have this paper that we just submitted. So you're looking at how good the fit improve as a function of the learning iteration. So if you think about the x-axis here is how much chess game you have played. So how much SED you have fed it. So you can see that as you play more and more chess game, you fill up the knowledge base more and more. And this leads to a better fit that is significantly better than just a native LLM. So because the native LLM is just a LLM without the knowledge. But here we are also not hard coding the knowledge. So we are just letting the LLM to interact with the James Webb data and using the inherent intelligence of the model to learn about that. And it's even more interesting that you can see like there's a plateau here. So you see that when you first do the learning, the chi-square is not improving. Why this is the case? So you can plot like the other metrics. So the blue line here show you how many band is well fitted by the models, meaning that within the SED, the different wavelength, how many wavelength are well fitted by the physical models. So you can see that as you first play the chess game, just like playing the AlphaZero, you first learn the policy in a network. So this is also what is happening in LLM. So the first few knowledge that you get is sort of what we call exploration. So you are learning the obvious. So you say, if I see there is an overestimated in the ultraviolet, I will change the star formation history. If I see there is a under estimation in the mid infrared, I will change the AGN. So these are sort of like rule of thumbs. You will improve the number of wavelength that being fitted, not necessarily improving the chi-square. But after you have learned the basic knowledge, so you kind of know what is the rough region of the models, then the model will start to do the exploitation, right? And this is also what we see in this, letting the LLM to interact with the James Webb data. So the point here is that I think there is a lot of hypes about AGI, right? So if you go to media, people always say the AGI is coming, there is Q-star or GPT-5. I don't think that is the point. The point here is that with the current models that we have, the LLM is not stupid, right? So they are somewhat intelligent. In particular, like in this case, they understand basic form of causality. So they might not be able to come up with the Einstein theory of a general relativity, but it does understand the basic causality through actions. So what do I mean by that? So if your mom asks you to sweep the floor, and after you sweep the floor, you see the floor is clean, as a human, like you would learn that through my action, this has leads to a clean floor. And the LLM is able to do that, right? So this is what we show, even by not letting it to know like anything, just let it to play the SED like a feeding games, it would gain the knowledge as the human would. And this, of course, is a very interesting thing, because just like Ashley mentioned, you can talk about the interaction between the human and AI. So now you have the agent that can, with enough like compute, you can play the game infinitely, right? So you can play the Alpha 0 infinitely. You will summarizes all your knowledges to your chess book. And you can also expect that maybe some of this summarized knowledge, even for a simple task, is more robust than the human, right? Just like how we play Go chess. But more importantly, of course, the human can examine the knowledge because these are all in the form of natural languages. So you can check the knowledge. You can even include your knowledge, right? So you can put your knowledge as natural languages and impose the prior knowledge. But all this meaning that just like a very experienced researcher, you do not need to feed all the parameters, right? So if you are a very experienced researcher, especially for transients, so you know how to upward and downward stuff. And this means that you are saving a lot of compute because you're using all these rules that you have learned to save the computational time. And why this is important? Because in principle, right? So as also like Ashley mentioned, we have a lot of sources, even without the transient. We have billions of sources on the sky, and 99.99% of them never get a study because they're deemed too boring, too simple. But maybe there are lots of anomaly inside this 99.99% of the objects that never get studied by a grad student because we never have enough grad student to feed all the SED, right? But in principle, the AI can. In principle, the AI can fit as good as a human could. And this could be game changer, right? So for this like particular thing, meaning that all the data that we collected, we might be able to reason about them, just like a human would. Then we will be in what, like Salman said, we are back to the data stuff of a regime because we have used up all the data. This, of course, is a very blue sky thought, right? So we show that this could work for SED, but even for SED, right, we have shown that this can only work with like a GPT-4 type of models. So you need to have a very capable models and still be able to run that fast enough and cost efficiently enough. And that is the problem. So how expensive is this thought process? So give you an example. So the SED like feeding that we have just shown typically costs about 100,000 token. You might ask, why so many tokens? Because there are many agents are working together and they need to discuss and come up with a new strategy. And those, because the LLM are not like super strong, this chit chat like between the agents are pretty long. And how much does that cost? If you take the GPT-4 models, it's about $10 per million tokens, meaning that this translate even for a simple like SED task, it will cost about $1 per source. You might say, well, like, is that a big deal? Yes, because if you take, say, the Euclid or Roman or even like LST, talking about billions of sources, right? So you're talking about billion sources. If each sources cost $1, then this costs $1 billion. So how much is $1 billion? $1 billion is like about the same build cost of this space telescope. So as you can imagine, if you go to your space telescope manager and say, hey, I want to double the cost to run the API, most likely he or she will not be thrilled, right? So meaning that we really need to cut down the cost by an order or two in order for this to be feasible. So what are the options here? How do we get there? So this is a third part that I want to quickly go through. So first of all, capitalism, yay, because there are lots of people are fighting for users. So there are lots of companies are building LLMs. But the question is that which one is good, right? So I think that's the problem. Like there are lots of interest in LLM for astronomy, but we never is able to benchmark that, like in terms of like astronomy, how strong these models are. So this is why with some of the people in Argonne, with Salman groups, we are looking into some of these benchmark data set. We have curated a astronomy specific benchmark data set I will not give you sort of the detail how we get there, but this is a typical like example. So this is asking why there is a number density drop for quasar at redshift of 5. It's a MCQ like question. You can think about this, the difficulty of this question are typical grad student like general exam like question. It's not that simple. Even for astronomers who are not working in that particular field, it might not be that simple for them. So with this benchmark, then we can start to compare the models. So what we are showing you here are the accuracy in terms of the MCQ, meaning that how many % of them get correct as a function of the cost, right? And the different line here is showing you roughly the trade-off of 10 times the worth of money. So if you look at this model, the GPT and Claude are equally strong, just that Claude costs slightly more and is slightly more accurate. But there are models like even the Google Gemini or the GLM. These are models that have shown to be very strong in the other benchmark. But for astronomy, they are not as good. In fact, they are orders of a magnitude not as good, meaning that if you use the Gemini, you are wasting 10 times the money. If you're using the GLM, then you are wasting about 100 times of the money for the same performance in this task. You can look at the cheaper version because just like the GPT have like GPT 3.5, all these models have sort of the cheaper version, but they just slide down the scale, right? So this line show that you can pay less, but then you don't get the performance that you want. So like as we have find that the GPT-4 is really necessary and non-negotiable, meaning that all these are weaker models, despite being like cheaper, they are not the right thing to do. So this is bad, but you can ask, well, you know, if you are in the position of, say, Salman, you have the Argonne and National Labs, then you might have a loss of a GPU, right? So you might not have a loss of money then, but in academia setting, it's much easier to ask for time in GPU than money, right? So how good the open source models are. So this is something that we also tested extensively, right? So like if you asked me 3 months ago, I would say that this is a no-go, right? Even 3 months ago, we are 10 to 20 points worse than like GPT-4. But things has changed, like especially this year, especially in the last 3 months. So if you now see some of the strongest models, like the Llama 3, the Q12, the biggest like Mixtro, they are almost as good as a GPT-4. And in fact, they are better than a Gemini and GLM for this task. So yay, right? So we can have open source models, but nay, because these open source models is only as strong as these closed source models, only at the 70 billion parameters. So what does that mean? Meaning that we are just trading off the insurmountable amount of cost to a insurmountable amount of GPU. Why? To give you an example, so if you run the Llama 3 70 billions, then it has a throughput of about 100 tokens per second for 4 GPU. This meaning that for one SED sources, you need to run the reasoning for about 15 A100 GPU minutes. It means that if you have a billion like sources from Euclid or Roman, then you will need to run about 10 million GPU days. If this seems too large to comprehend, meaning that even you give me a cluster of 1,000 GPU, like POSI, I still need to run POSI or NCI for 30 years, right? So nay, because the open source model seems good, but they are not scalable at this point, right? So this is why it leads to a lot of things they have been working on in the last 6 months, understanding can we fine-tune a large language models to do well in a specific task? Like, can we use a smaller like models? It's generally not as strong, but maybe it's good enough to do some of the tasks that we want for the agents. And this is why we started to work on this. That used to be called the TBD, and some of you might know, but the core group has moved on. So we now is called the Astro M Labs. Who are they? So there are a bunch of people from the ADS, from Harvard. There are people from the Oak Ridge. There are also like people from the Argonne lab that are working on that. We've also the people at UIUC. So we have a lot of like support, including from NCI, from Gaudi, from POSI, but also from the US, from a Frontier. And we spent a lot of time to learn this, right? So basically, we have not like released like many models, but most of the models that you have in mind, we have trained that with all the astronomy archive. But we didn't like release that because we find a very interesting thing, which is for the very strong models, right? If you look at the state of the art small models, like if you train them, then they become worse. Like it might seem to be a good idea to train them, but for most of we can see, it actually become worse because the models are quite brittle. You can stay the same if you have a bigger model, if you have a 70 billion parameters, and if you have the support from Frontier, you can fine-tune that and doing the continual pre-training, but it just leads to the same performance. So it's not making things worse, but it's not like improving. You can talk to me why this is the case. I think we have some theory why this is the case, but the point here is that this also seems to be not very scalable. Most of the LLM seems very brittle. Maybe we are doing something wrong. We would love to work with the industry like expert on that, but yet we have not seen any significant gain. Again, that despite a lot of interest, like a lot of talks, but most of them seems to be mostly just aspiration, right? So what should we do, right? So it seems like we have a very cool idea. We can reason about all the sources, but we are too poor to do that. So what should we do? I will start by quoting Warren Buffett. The trick is when there's nothing to do nothing. Or there's the reason to do nothing is because, as Warren Buffett say, the stock market will is designed to reward the people who are patient. Why this is the case? Because you have to trust Jason Huang, right? So the NVIDIA is growing. A lot of the company is doing like GPU. The GPU compute is exponentially increasing, meaning that the LLM is exponentially become cheaper and cheaper over time. But how fast, right? So how fast the price is doing. So the question the student might have is, should I do that now? I only have 3 years or 4 years for grad school. The answer is yes. So if you look at the benchmark that we have shown, like remember this line here, show you the price is dropping by a factor of 10. If you look at Claude, within 6 months from July last year to the March this year, it dropped by 100 times, meaning that for a given performance, the models that you are running now is in principle 100 times cheaper than 6 months ago, right? And this is also applied to all the company. And you might say, well, this might plateau because we are getting stronger. No, because Claude just dropped their latest model. So this is Claude 3.5 Sonnet. This is 3 months. Again, in 3 months, is improving equivalently. The price is cheaper by 100 times. Meaning that even in the most conservative limit, the pricing e-folding time is about 3 months. So things that will cost you $1 billion today, in a year, will cost less than a postdoc, right? So that's the summary that I want to just like, of course, that this is more like blue sky, but I want to talk about, so what we have discussed today is that we try to quantify what is like going on in AI for astronomy. And the way that we did that is through the knowledge graph. I think that there is a lot of hype, but there's still a lack of innovation. And in particular, right, I think all the things that we are doing are great. I'm not saying that like all these are not great, but just that a lot of things we are still using AI as a tool instead of, as the Peter lesson say, we should create the type of thinking that could scale up to infinity. And the way that you can scale up to infinity is not focusing on individual tasks, but rather building up a methods like using LLM for for reasoning that could scale up. You can say the example that I show is very simple, sure, right? It's an SED like feeding. It's not that complex, but you really show that the LLM like agent even now have the ability to distill some of the basic causality. and that will change how astronomy is done, because you can done end-to-end like a research in astronomy. But of course, the problem now is just how to do that at scale and fast enough. But with the speed that we have been seeing, this like amazing speed that no one has seen in the history of the humankind, that either the performance and the dropping of the price of the prices, I just want to remind you that like not too long ago, there are very few people can have a cell phone, but we all have a cell phone in a few years, right? So, and this is, I think, what is perhaps one of the more exciting things that I believe that could happen in AI for astronomy. I will stop here and take any question that you might have.
That's great, Yuan-Sen. That was a really intriguing talk. So just looking at the Q&A tab, we've got no questions just yet. So I'd encourage the audience to either enter their questions in the Q&A tab or to raise their hand. I was intrigued by this university TBD. I've heard about that before, but don't know a lot about it. And I see it's turning into Astro MLab. Could you talk a little bit more about that and maybe how people could get engaged if they're interested?
Right. So I think the UTBD is still there. I think just the mission has split a little bit. So used to be there is the community like a building part, but there's also the model like training part. So the Astro MLab is focusing on the training of the models, right? So more like the sciencey part. So this is why we thought we want to be like move fast with a small group. People can engage, right? Like people can reach out to me, like if you want. There are lots of it's great to have more people to be excited about this idea. Not even just doing research, just understanding how to build a agentic like research, right? How to build a end-to-end like pipeline for some of the tasks that you need to like repeat like many times. And most of them, like if that part cannot be done with a simple like, optimization, then yeah. So we really encourage people to do that. Like it would even be great to have some form of like workshop, to just brainstorm.
Still waiting for questions. But one thing struck me as well when you were talking about the large language models and ChatGPT and the like. And you talked about working with those companies, or to what extent can you work with those companies? Is there enough in there for them to want to invest in astronomical research?
Yes and no. So we did talk to a few company. There are places that are more like receptive, but the challenges here is that the investment that we have, like especially for individual group, is too small to entice them. Even you say, we can do this for my project for 100, 1,000, or even like a small grant, most likely they would think it's too small, right? But if you say we have like SKA like data, or we have like Euclid or Roman, so this will be more bigger scale, and this is the part where I think the management will play a big role, because like this is beyond individual like researcher like ourselves in Astro MLab that can change, but it requires the management to realize that this is a path. Yes, we are asking maybe now like 100 like millions, but it's a path that is worth like doing.
Yeah. Okay. Yeah. We've got some questions now. So Min Hyun said, "Great talk, Yuan-Sen. Astronomy data is getting very big, as you said. For our work, is the contextual or token limit an issue now? And can you comment on the potential for larger token models for astronomical discovery?"
Yeah, so the thing is, it really tied to, so it depends on what task you are doing, right? So for the different like agent, why we break that into like different agents, because some of that require longer context windows. Like if you want to like retrieve like information and like propose new action, then you need a long contextual like windows. But in many cases, it's not really that limited by the context windows. It's really about the strength of the LM. So the current limit, why we need so many tokens, is really like individually the LM is not very strong. It's just that you have a bunch of younger students, and how do you make best use of them, right? So you need to break tasks into like the really like less specific tasks. Of course, if you reach to AGI, then no problem. You just say fit the SED and reason about the SED, right? And that is why humans are still has an edge, because we have a very effective way. But the fun thing about what we have shown is that, yes, the LLM is not like very strong, but you can help them. You can let them to remember what works. Just like, okay, your native thing. Yeah, so that's the point.
Okay. Any more questions for Yuan-Sen? As I said before as well, you can raise your hand. Oh, there's a question in the chat, actually. So, Humin Chu asks, do you believe AI can do science, for example? There's symbolic regression to guess the physics relations for different variables by learning from the data. Do you think AI is doing science here? And what's the difference between this mode and the mode you mentioned in the talk?
Right. So I guess this depends on your prior belief of what is the fundamental causality structure. My own belief, which is also like restricted to my own belief, is the knowledge that we have in astronomy are quite often more fuzzy than a symbolic. It's a part of the thing that we should aim for, but I don't think it is a very big set of the causality that we care about.
Okay. Any more questions for Yuan-Sen? If not, well, if you do have any questions that strike you before the end of this showcase, you can maybe raise them during the panel discussion, which we'll have at the very end. But yeah, so I'd like to thank Yuan-Sen again for that really great talk.
Right.
And we'll now move on to our final speaker for the day. So it's my pleasure to introduce Peter Nugent. Peter's a senior scientist and division deputy for science engagement for the Applied Mathematics and Computational Research Division at Lawrence Berkeley National Laboratory. He currently runs the largest astrophysical transient discovery pipeline created to date, the Palomar Transient Factory. Over to you, Peter.
Thank you very much for the introduction, Chris. So I am going to sort of follow on a bit from what Ashley and Salman were talking about, but with a very different view, which is the look at astrophysical surveys, like what's going to be coming up with Rubin, and how machine learning has impacted them over the years, and sort of where we are today right now. So with that, I will share my presentation. And there we go. What I'm going to do here, I'm going to shrink you down. There we go. Okay. So first off, what is a supernova? So for those of you in the astro community, you probably know this well. For those from the machine learning community, a brief overview: bright and powerful explosion of a star. They're amongst the biggest explosions in the universe. Material comes out from the explosion at 10 to 20% the speed of light. They outshine galaxies made of hundreds of billions of stars. In 1 month, you know, it's going to emit more energy than the sun will in its 10 gig-a-year lifetime. The term was coined by Fritz Zwicky in 1926. The Chinese, many centuries before, called them guest stars because they came and left. Supernova have been observed for over 2,000 years by humans, recorded observations. Somewhere in the observable universe, you have a supernova exploding every second. And in a galaxy like our Milky Way, we have one supernova every century, although the last one in the Milky Way was observed by Kepler and Galileo in 1604. So Ashley talked mostly about core collapse and other powered supernova. I'm going to focus in on type 1a supernova. So what is a type 1a supernova? Basically, it is a supernova that lacks hydrogen. That's where it gets the 1 from. And the A means it has a strong presence of silicon in its spectrum around 6,100 angstroms after it's been blue shifted towards us because it's traveling around 10,000 kilometers a second. There are a couple modes that we think a type 1a supernova can be born from its progenitor system. One is a single degenerate system, and here's an artist's rendition of that, where you have a white dwarf accreting material from a star, a main sequence star, a red giant, which has filled up its Roche lobe, and it pulls that hydrogen over, and then it slowly burns it to carbon and oxygen. And as it approaches the Chandrasekhar limit, the carbon ignites in a runaway thermonuclear explosion due to the densities and temperatures rising at the core as the radius keeps shrinking as it gets more massive due to the quirk of quantum physics and special relativity that Chandrasekhar discovered almost a century ago. Another potential system is what we call a double degenerate system, where you have two white dwarfs. They either merge, or the more massive one pulls helium from the smaller one and undergoes what's called a double detonation, where the helium ignites on the outside, sends a pressure wave down to the center that jacks up the temperatures of the carbon and oxygen, and you get another detonation. So how do we know this? We infer it from observations, since we see supernova in old galaxies where no star is more than 2 times the mass of our sun, so it can't become a core collapse supernova. And the fact that there's no hydrogen nor helium in the spectra of these supernovas. So something must be going on with a system like this. And back in 2011, as part of the Palomar Transient Factory, we discovered a very interesting supernova with very, very early in its light curve. And what you see here is what happens when the supernova runs into its companion. And you get a light curve depending upon your viewing angle that kicks off and then increases in brightness very rapidly as the supernova slams into the companion star. And so if you're looking directly on it, it's very bright at first, and then it fades away as the supernova covers the companion star. And if you're at a 90-degree angle, you get a little bump, and then it goes up. Well, 2011 FE, we had a non-detection just a few minutes after explosion, and I'll try to 3.92 hours after explosion. And because of that, we were able to constrain the radius of the companion of the star itself, and the star was limited to about 0.02 times the mass of the radius of our sun. So because of that, the only thing that it could be was a white dwarf. And here's a very nice plot from Bloom et al. 2012, which shows basically the space ruled out by HST observations, the space ruled out by our density and radius limits, assuming that there was about a solar mass of material in the explosion. And basically the only thing you're left over with are neutron stars and white dwarfs. And since a neutron star can't produce a thermonuclear explosion, all you're left with are white dwarfs. So what's interesting about the type 1a supernova is that they're very similar from one to the next. And the differences between them can be calibrated out to where you can make a distance measurement based upon their brightness to 7%. And so this is the follow-on survey to PTF called the Zwicky Transient Facility. And this is what they discovered just in June to July of 2018 on the left. And here are the light curves of all of these supernovae in 3 different bands, G, R, and I. And when calibrated, and now they're coming out now with a new paper, and this is the decline rate, how quickly the light curve drops from peak brightness in 15 days versus the peak luminosity. And you can see, while you have a handful of weirdos that are colored here, out of about 3,000 supernova, 2,800 of them in gray have this very nice tight relationship between the decline rate and the peak brightness. And so because of that, these are used as standard candles for cosmology. And for the past 25 years, we've been making observations of type 1a supernova at both high and low redshift that shows that the universe is currently accelerating, and 2/3 of it's in dark energy. And it's a very straightforward measurement. You're looking at relative brightness, and you're looking at redshift, which is the expansion since light left the supernova. And what we see is these supernova are fainter than we expect. So something's causing the universe to expand beyond what we normally thought. So because of this, there was a lot of interest in supernova when this calibration was first discovered back in the early 1990s. And while the discovery of the acceleration of the universe was done in the late 90s, things were a lot easier back then. And here's a picture of the Workhorse telescope for a survey back in 1998, the Victor Blanco. And they had one 2K by 2K CCD, and eventually they upgraded to something called the Big Throughput Camera, which had 4 of these. We could transfer everything up from Chile on a 56K baud connection, so very similar to the old modems of the 1990s, during the night, and subtractions would be done at dawn, and we typically took 5 to 10 minute long exposures. And then follow-up observations were triggered all over the world and from space. And so this is sort of how you find supernova back then, is that we would look around new moon, and so you'd have a reference image there, and then you'd come back just before new moon and you'd subtract the image. And we had 50 or 100 fields, and there were about 1,000 galaxies per field. And if you do the math of how many galaxies do you need to look at to find one supernova, if a galaxy has one supernova per century, you need to look at about 1,200 in order to find a single supernova. And then once we found it, then we'd get spectrum at the Keck Observatory. We'd trigger the Hubble Space Telescope, telescopes on the Canary Islands, Chile, in New Mexico and Arizona. And all of this was fairly straightforward. And humans were doing everything here. So per image, we would have about 200 5 sigma detections. And because of asteroids, we take 2 images and we look to see if something moves. And so we require 2 independent detections to call anything good. We only had about 50 to 200 images taken per night, about 4 degrees of the sky. And we made cuts based on the shape, on motion, and a human scanner would have to typically look at 5 candidates per image. So if you're only taking 200 a night, and they're about 5 or 10 of us looking at the image. It just took a few hours, and we weren't interested in getting any faster than that, because we had the sort of day to do this before we got on Keck to try to take a spectrum. Around the year 2000, we decided that, well, we found all the high redshift supernova we needed. What we need to do now is find low redshift supernova. And so we started working with a group called the Near Earth Asteroid Telescope, NEAT. And they had a few different sites at Haleakala and Palomar. And if you just think about it very simply, the volume of the universe in a CCD image is much greater at high redshift than it is at low redshift. And so in order to find supernova at low redshift, you have to search a lot more sky. So we were starting to get up to about 2,000 square degrees a night, 28 gigabytes per night. And this is just an ungodly increase in the total amount of searching that we did. 250 times increase per night compared to what we did before. And this was every night. And so this was not really tenable because we could not go from 5 or 10 scanners to 1,000 scanners. And so what we started to do was explore machine learning, as it was back in those days, to try to find more supernova with less work. And so we started looking at boosted decision trees, random forest, and support vector machines. And the boosted decision tree, basically, we had labeled data, the supernova that we had found, and we'd go through and pose a series of questions. Was the signal to noise greater than this? Was the motion less than that? Was the shape of the object less than a certain amount? And we'd look at various combinations of these, and that had a profound impact on what we could do. And so we started to run these tools in the early 2000s, and we started to be able to keep up with the surveys to a point. And we were only running these for 2 to 3 months at a time because it was just too much work at that point. And shortly after that, we said, okay, we've got to do a dedicated facility for doing this. So Sri Kulkarni at Caltech had this idea for the Palomar Transient Factory, where the goal was to discover transients on a whole bunch of different time scales. And this included novae, this included long GRBs, orth and afterglows, Corcolat supernova, type 1 supernovae. You know, we had a laundry list of things that we wanted to look at, things that evolved on daytime scales to things that evolved on 100-day time scales. And the discovery engine was the Palomar 48-inch, but the cool thing was we had set up the Palomar 60-inch for immediate follow-up, and we had lots of other follow-up facilities, but that one eventually got triggered without humans in the loop, and I'm going to explain how we wound up getting there. So this is the imager that we had, 92 megapixel camera, 1 arcsecond resolution, got to 21st magnitude in 60 seconds, and we did 300 of these exposures a night, plowing over the sky, repeating every night for 30% of the fields and every 3 to 5 nights for the other 70%. We had a whole bunch of projects, like I mentioned, and so you can see sort of the key projects there, and a ton of follow-up facilities. And this is what really made PTF very successful, was that everybody was invested in everybody else's science, and we pooled our follow-up resources just to do the best science. And this is what accelerated everything. But we had a major challenge, which was we still had to get to good supernova, and now the science was pushing us to do this faster and faster. If some of these things faded in the night, we couldn't wait for boosted decision tree and scanners to look at it in the morning to say were things good or not. And so our pipeline sort of looked like this, where you have Palomar 48-inch, puts its scheduler together, has its observatory control system, the cameras going, there's data quality monitoring, and we had a very high speed link through a microwave relay tower down to UC San Diego that then took it up from there to Berkeley lab. We did the real-time processing at Berkeley using the National Energy Research Scientific Compute Center, where we did image subtraction and classifier. And then we threw the discoveries back to Caltech on something we called the Marshall. So by the end of the survey, we went through 2 million images. There were over 40,000 reference images made over 20,000 square degrees of sky. We had 1.5 million subtractions, over 1 billion candidates, and 50,000 saved transients, and many more unsaved. And we did this in 851 nights, and the database was over 1 terabyte by the time we were done. So this is what PTF wound up finding, over 3,000 spectroscopically typed supernovae, and the majority of them were type 1a because they tend to be the brightest ones. But we also found hundreds of thousands of galactic transients. We found tens of thousands of transients in the Andromeda galaxy. And the collaboration wound up producing 209 publications, including 7 in Nature and 3 in Science, that were based a large part on what we were able to do with real-time turnaround. And so every night, PTF produced about 1.5 million candidates, and most of them are not real. A lot of them are image artifacts, misalignment of images, image saturation from bright stars. You'd find about 50,000 asteroids, a couple thousand variable stars, 100 supernova, but most of them you already know about, and 3 to 4 new young supernova or other supernova-like explosions. And this is sort of what an image, a reference, new in the middle, and a subtraction. And so 1.45 million out of the 1.5 million typical objects seen per night were these subtractions. And here you can see a beautiful supernova. But if you look at that image on the far right there, you can see all the other junk in the background. And this is a rather clean image. It only had about 200 other detections on it. And so we would have to weed through these. And so how did we do this? Well, we started the program by doing subtractions and having scanners like we used to. And we employed some of the same boosted decision tree cuts that were in there, although we allowed the user to go in and change these and see if they could find things. And then when we found a supernova, that was great, because then all follow-up, all subsequent images, we knew that there was a supernova there. And so we could use that as a set of real supernova discoveries. So for the first 3 months of PTF, we had real-time scanners going through, collecting the data, marking things up, using these boosted decision trees to weed out things that were highly implausible, and then start to fine-tune it. And when we were done with that, we had a collection of a whole bunch of good supernova, and of course, a whole bunch of garbage as well. And so we took that and we turned it around, and we had good detections and bad detections. And we threw this at about 20 odd scanners now that we had labeled data. And we basically asked them a question by looking at some of these values and saying if something was bogus or something was astrophysical. And if you couldn't make up your mind, you could skip it and go on. And we had the scanners go through several hundred of these things. Now, the thing is, not everybody's a good scanner, and everybody comes in with their own biases. And that was one of the things that we started looking at. It turns out some people are very, how shall I put it, optimistic. They hope everything's a new supernova. And so they, compared to everybody else, will call more things real than are actually real. Then you have people that are very conservative. They only want to see something that looks like it's beautifully on top of a galaxy. Its signal to noise is like 20. And so they're very pessimistic. And we can actually use that information and tune it up and determine what their biases are and put everybody at the same level, and then use that to train a classifier. And so we trained a random forest to generate scores based upon all these classification scores that we gave it. And I'll go through later as to exactly what we did there. But here are some examples of things that are good. Anything, I think we, in this phase, anything above 0.1 was considered a real object. And so here you can see something with a slightly low real bogus score of 0.2 and something much higher at 0.7. And so this is how we started labeling the data, and this we called RB, real bogus. And this was actually the first implementation of the real bogus. And so what we were able to do is, instead of wait till the next morning when we have the scanners go through looking at the boosted decision tree, we could actually apply this random forest to the data, and we'd get turnaround that was sort of between 30 minutes to an hour after the observation was taken. Median turnaround was about 30 minutes. And this started opening up a lot of great science for us, because then we could start thinking about triggering observations, not only the next day, which is what we were currently doing, but even we could start thinking about observations being done in Australia when the sun was going down as it was coming up on Palomar in San Diego. And so we could actually get observations that same night. And then if things got really good and we trusted this without a human looking at it, or even if we had some humans in, say, Europe, where it was their daytime, who could look at the feed coming in from the pipeline, they could trigger actually during the night in the Northern Hemisphere, in North America or in Chile. So then we said, well, we need to improve this. And why do we need to improve it? Because it worked, it was pretty good, but we knew we could do better. And so what we employed next were citizen scientists. And we started a project called Galaxy Zoo, the Hunt for Supernova. And this got up and running in 2010, shortly after we got our first RB1 trained. And what we were trying to do was get these people to go through and do what our scanners had done, but during the night. And now we were fairly confident we could send them pretty good candidates that were cleaned out by our RB1, but not perfect still. And so we just asked a set of 4 very simple questions. Is there a candidate sort of located in the crosshairs? Does the candidate look like it subtracted correctly? And we gave them images on a training page of sort of what was good and what was bad. And then if there was something bad with the subtraction, we'd follow up and we'd ask, what was wrong with it? If it looked good, we'd say, is the candidate star-like and approximately circular? And did we see the candidate near a galaxy? And so we had 1,200 people go through all of our previous data between August 1st and August 12th, and they were able to do that in 3 hours. And the top 50 things that they got were all supernova and variable stars, and they found 3 of them before we did. So they were getting better than our RB1, and they were doing it quickly. When we had things up and going, we had folks finding about 250, they'd go through about 250 of these a night, and we had 15,000 users at peak. So we could combine all of this power to say, well, 95% of the people thought this was a good supernova, and lo and behold, almost every single time it was. Now, the other great thing was they now gave us a much, much larger data set of labeled candidates. And of course, once we found a supernova, we could tell from its light curve how it went up and down that it was actually a true supernova and not something else. So this added to this. And so now all of a sudden, in 1 year's time, we were able to greatly boost the amount of labeled data. And so there was a nice paper written up, and where we thanked all of the 15,000 users that went through. And for this, we were able to train our next set of real bogus classifier called RB2. And you can see where our training set size was just about 1,000 in total, with only 75 real events when we did the first RB1. We now had 78,000 objects, all due to what the citizen scientists were able to label for us, and all confirmed to be, bogus or real. And we had a much larger sample of real objects, now 15,000, so a much larger chunk of our data set. And we were able to move with a new implementation in Python where we could run this in real time rather than doing batches of sort of 100 or 200 of these things. And so with this, they were able to start looking at how things improved. And so here you can see the misdetection rate at 1% false positive rate. So 1% sort of throwing out 99 bad objects out of 100 to get 1 gave us a ratio where we were basically able to trigger on real things all the time. They did a very interesting thing. They started with the full model at the bottom and then iteratively eliminated the features whose absence yielded the best 5-fold cross-validated figure of merit. And they stopped when their figure of merit was no longer defined, when the ROC curve no longer went below false positive rate of 1%, with only a few features left in the model. And so they sort of did this bootstrap iterative approach with 20 out of the 40 features, where they could do this in about 610 steps. So you couldn't test every single one of them. That would be 10 to the 11th steps. But they get a nice improvement of their figure of merit in terms of the misdetection rate by removing features that were extraneous. And what was great was, and you can see the curves here, the ROC curves, the false positive rate versus the misdetection rate. The ML-Zoo was significantly better than the human zoo citizen scientists. So we, at that point, retired ML-Zoo, much to the consternation of all the people that were doing it there. And we also wanted to have a little fun. And so this is not a slide I put up, but I just speak to it. We sort of wondered why they had this large bump in the middle. And so this is back in 2010. And back then in the UK, pubs called last call at around 11 p.m. at night. And it was very common for people to grab a couple pints at last call and down them before they got kicked out. And interestingly enough, it seems that a lot of people then went home and wound up scanning. And so the majority of those subtractions occurred within 1 to 2 hours after last call in the UK pubs. And since this was a majority UK project, things got a little bit worse at night. So it was nice to implement this new entirely human-free approach. And the other cool thing about the approach was that, of course, it's repeatable. You give it the same thing, it comes back with exactly the same score. Not so with the citizen scientists. They were also able to show that their classification methodology was insensitive to mislabeled data, which is huge. Because you often do, even if you know that there's a supernova there, sometimes an asteroid goes right next to it, or sometimes a bright star will become saturated and run over where the supernova was in one image and not in another because there were some clouds the previous night or the seeing was better. They also showed that their the score was very stable up to a magnitude of about 20. And that for supernova, the score was good even when the contrast ratio between the supernova and the galaxy, as it gets fainter and fainter after explosion, got lower. It was fairly good. So with that, we now had something that could really smoke in real time. Literally took a second to run on our images. And so at that point, we turned around and looked at our entire pipeline at NERSC to test the speed of everything, pulling the data from the telescope, I/O, subtraction software, how we ran the RB2 algorithm, how we loaded the Python libraries to get it up and going, loading the database, everything like that. And what we were able to do, and now this is on a log scale here, was reduce the time for the vast majority of the observations to under 5 minutes. And so now you can basically say with strong confidence, 5 minutes after an image was taken, that something is real. And we looked at a lot of interesting things with this, and we actually applied some machine learning to find correlations and new bottlenecks. And some of it was simple, like, when you go stare at the heart of the Milky Way galaxy, where you have 10,000 stars on every image, you're going to find a lot of things, and that's going to slow things down because you got to load the database, you got to run the RB2 on everything, all of that delays things. Some, and that's sort of the plot of down on the right there, the number of candidates versus the time for the typical one versus the median one that we found versus some that were in much larger fields, much more dense fields. The plot on the left shows the time in seconds for data to get from the Palomar 48-inch to NERSC. And this we looked at and we were like, why does this correlation happen every single night? It looks like this. It's slow in the beginning of the night, and then it picks up speed and gets quite quick, only about 140 seconds to move an image. And then it increases again right before dawn. And the microwave relay tower that we had, and this was only discovered after we started looking at the correlations between all the data and all the other data, we realized we were fighting for bandwidth from the casinos that are located out in the hills between Los Angeles and San Diego. And so at the beginning of the night, they were live streaming horse racing from Hong Kong. And people were watching that, and then they shut those things down around 8, 9 o'clock. I guess the races were over or whatever. And then you got to kick up again in the morning when people started going into school and doing online learning and things like that. And so some of the things we couldn't compete with, but it was nice to see the correlations. Now, what did the fast turnaround do? Well, it enabled a ton of new science. And so here are some examples. So there on the far left, you can sort of see one of the challenges. A GRB goes off and it has an uncertainty error box of almost 100 square degrees because it was poorly localized. And so we wound up taking a bunch of images with TTF, basically a target of opportunity using the telescope to map out the sky there. And we were able to find a new candidate that night. And the hard thing about these afterglows is sometimes they're very quick. And so here's an example of that. You can see this one where on the right, where we have a non-detection at 1.45 days before. And then we had 3 detections that night, and you can see it dropping very quickly. And we were able to turn around that night and get a spectrum of it. And then later, we discovered that the interplanetary network of gamma ray sensors found a GRB with a localization of 200 to 300 square degrees, 15 minutes before our first detection there. But all of this was enabled by being able to turn around incredibly quickly. Another example is something called flash spectroscopy. So here we found something and triggered Keck telescope because it was rising so quickly between the first and second observation. And then we were able to trigger SWIFT that night. We were able to get an observation that same night. We were able to trigger the EVLA, triggered Karma, a whole bunch of things. And what was incredible about this was we now used it as a tool for something called flash spectroscopy. So here, this is for a core collapse supernova. If it goes off in an environment which has a lot of circumstellar material, the very first thing you see is sort of that circumstellar material. And so here we have a spectrum of this event. IPTF 13AST, also known as Supernova 2013 CU. And you can see these strong emission lines, which represent basically what look like Wolf-Rayet stars. And in fact, this was a Wolf-Rayet that had exploded. But what we get from the supernova is when that bright light comes out, we're lighting up that environment. And so we got to see what the progenitor looked like from the light flash that was bouncing off the surrounding material. And then later on, as the supernova expands and sort of overcomes all that circumstellar material, we can see the underlying supernova itself. And so that was enabled. Now, we now have this in hand. Things are running smoothly. This set the stage for the Zwicky transient facility, which is still running to this day. And a lot of these tools and techniques are being employed in LSST. And people have moved on from the random forest to convolutional neural nets that can do this just as well, if not better. And so that's fairly smooth. And so the art of discovering transients is sort of one of these things where machine learning has been going for the past 15 years. And that's basically a solved problem. The next challenge is more in line with what Ashley was talking about. And I'm going to talk about the spectral analysis of the supernova after you find them. So here's the spectrum again of a type 1a supernova, and spectra tell us about the structure. The composition of a type 1a is mostly intermediate mass material, and here you can see the lines. calcium, silicon, sulfur, magnesium, iron, there's cobalt in the spectrum as well, oxygen. We see those things. And they're made up of blended P Cygni features that are traveling at high velocity, 10, 20,000 kilometers a second, and high ionization. They're singly, doubly, triply ionized features all through the spectrum. And there are millions of lines in the spectrum. Now, here is something called synapse. And synapse is sort of a brute force optimization to fit, using radiative transfer, the spectrum of a supernova. And what it does is it runs this code called SynOut, which takes about a minute to run, and compares it to the spectrum. And if it's a good match, it notes that in its optimization. If it's a bad match, it flags that. And then it goes and runs another one, adjusting these 50 parameters each time. And it basically has a range that it can adjust them in, but it's a very large range. And so what you're looking at here is a time sequence in which we did not have many parameters in here, 11. We were fitting 11 ionic species. And this run took about 20,000 calculations of SynOut in the Synapse framework to generate this best match. And at the end of the day, what you get out of this is sort of what species are there, how strong are they, and what are their velocities. That's basically what you wind up. Now, if you think about the computing time required to do that, we were basically running on 128 cores of one of the NERSC supercomputers at the time. And we would run it for about 12 hours to do a single fit to a spectrum. And once again, that's the information that came out. So this is nice. It helps you compare apples to apples, oranges to oranges in the supernova spectral field. But it doesn't really get you back to one of the questions that I raised in the beginning, which is the progenitor system. And so I mentioned that there are two, maybe more progenitor systems, two basic ones, but then flavors on top of that. So how can you go from something like this with the spectra to answering that question? And so here are the sort of different types, the 4 different types of potential progenitor systems. Like I said, you could have a merger, a violent merger. You could do this double detonation thing. And then for a delayed detonation, this occurs in sort of the Chandrasekhar mass accreting material over from the companion star, usually hydrogen. Or you could have what's known as a pure deflagration, so no detonation involved. And these are sort of all the models for all the various types of systems. And you can see, are they single degenerate? Are they double degenerate systems? And then how is the flame propagation handled? And these are really the questions that we want to answer. So this is where machine learning came in the next time in a very, very big way. And you know, what we're dealing with is sort of a parametric eject model. You know, we have all of the elemental abundances. So people run these explosion models, any one of those explosion models that I showed you back there for any of those progenitor systems. And what they get out are the elemental abundances in how much mass do we have in each of the objects, their densities, their temperatures. We assume homologous expansion. So this basically means that after the first 60 seconds of the explosion, the fastest material is on the outside, the slowest material is on the inside, and the velocity scales like the radius. And so then you can just basically say, well, the density will then drop like time cubed after that. So it's a nice approximation and turns out to be a very good one. The supernova type 1As are a lot of observations of polarization from them. They're very, very lowly polarized. And so an assumption that they're spherically symmetric is good. And now, instead of doing the 50 parameters that we had with our synapse model, we have thousands of parameters to model the ejecta. How much of this material do you have here? How much do you have there? And so here's, you can see sort of a simple animation of the material in the ejecta, where you have the unburnt material in black. So that's carbon and oxygen that remains. Then next in, you have sort of the material that's just partially burned. So this is your calcium, your silicon, etc. And then in the core, you have all this iron peak material. But for each of those explosion models, they can be quite different. And so you get out plots that look like this, where you have, here's the carbon, oxygen, magnesium, etc., where they exist in velocity space. And from that, you can basically calculate your spectrum. And so that's what they do. And they do that with a program called TARDIS. TARDIS produces a synthetic spectrum for them, very much like our SynAll code does, but it uses as input these explosion models. It's a Monte Carlo radiative transfer code, which self-consistently solves for the radiation field, ionization, and excitation balance. And a single TARDIS run, unlike SynAll, requires about 1 hour to run. So it's a beefier code, but then it can directly relate you back to exactly what is the material, how much of it is there, how hot is it, etc., in a self-consistent way. And it uses the photospheric approximation so that at some point you have a hard photosphere. So it's basically good for the early phases of a supernova explosion. And so this is what you go to. You basically then can feed it a model. Hour later, it can crank it out. Now, if we were trying to do something like Synapse, where then you compare to a single spectrum, now I've taken a problem that takes 128 cores and 12 hours, and I've made it at least 60 times more difficult. But we want to do better than that. And so this is where deep learning came in. Now, here is an example of what happens as the supernova explodes and expands. It gets brighter. You can see it's hot and blue, and then you can see how the spectrum gets redder as a function of time, and the velocities get slower. Okay. Now, there's not only information in the single spectrum, but there's a lot of information in a time series of spectra, because as that atmosphere expands, the densities are dropping and you see farther down into the supernova. So it's very much like a CAT scan of what's going on in the supernova. And since we know it comes from one of those models, you can use multiple spectra to simultaneously fit for the outer layers when it's very early to the inner layers when it gets later. And all of those have to agree with each other. And so that is something we never did with Synapse, which is try to fit multiple things, because it was just tuning parameters, and those parameters could be even unphysical compared. But with TARDIS, it actually has physical meaning. So then the idea is, okay, well, not only do I want to do one spectrum, but I want to do maybe 10 spectra at various times, from a week after explosion to 10 days after peak brightness. And so now I've taken a problem, like I said before, which is 60 times harder, and I've made it 600 times harder. So this becomes untenable. So the idea here is to start looking at Bayesian inference. And so we have a likelihood function that compares data to the synthetic spectrum. We have a prior distribution from all the explosion models. So it provides a space of model parameters that we can test. It's a very large space though, but it's at least semi-constrained and it's physical. And then we can sample a posterior probability distribution of the model given the data. And so the number of samples scales exponentially with the number of parameters. There's a lot of parameters, but this gives us a path. The question is, how can we do this quickly? And this is what a student, Jack O'Brien, who's just got out from Michigan State University and is now headed to Urbana-Champaign. He created a deep learning emulator from TARDIS. So the idea is to treat TARDIS like a function to map input parameters to output spectra. Neural networks are universal function approximators, so that's great. And we draw random parameter samples and evaluate them in parallel with TARDIS. So it requires a lot of TARDIS runs based on a lot of input training data, but it becomes an incredible tool once you've done that. So I think they burned about 500,000 hours, well, in various versions of this to train it. But they were then able to train the neural network to map out these input parameters directly to the output spectrum. And so now you can get rid of TARDIS and substitute the emulator for the radiative transfer during inference. And the emulator is 1,000,000 times faster than TARDIS. So now I've taken that problem, which was requiring 12 hours on 128 cores times 600, and I've done something which I can do it incredibly fast. And so in a paper that's coming out this year, he can fit time series of spectra self-consistently and derive with the uncertainties the underlying explosion model. And what you're seeing here on the bottom is all of the mass fractions for the various input models and their velocity ranges. And you can see the TARDIS spectra from the deep emulator that is run to fit that spectrum and how it hones in on the correct solution quickly. This entire run here that we're looking at took about 20 seconds to do. It's 4 times slower than what I'm showing you now in real time. And what you can see are not only the observed spectrum of 2011 FE here, but you can see the plus or minus 1 sigma error bars on that spectrum, given the uncertainties in the deep emulator that they created for TARDIS. So it has not only that, but then given the uncertainties in the spectrum, you can go back and say, what are the uncertainties in my final mass fractions? And what they showed for 2011 FE is that it is extremely consistent, sort of at the 99.9% level with a sub-Chandrasekhar double detonation model. And that's also very consistent with all our observations of this object. So what's next? Well, I think Ashley hinted at this in her talk. LSST is going to find a lot of objects in the Palomar Transient Factory and the Zwicky Transient Facility. PTF, we were able to get 3,000 spectra. ZTF has automated that. They've got 10,000. Unfortunately, once you go to a telescope the size of Rubin, you can't get that follow-up. That's impossible. And we'll have this light curve data coming out. So what I see are more efforts like what Jack has started with the Type 1a supernova and fitting the progenitor model. But we can also do that with photometry. It's not nearly as good, but you can use it. and you can go directly back to these are the range of progenitor models. And then you can start pulling in some of the tools that Ashley talked about. And you can fold those into saying, okay, well, if I know something about where it was born in its host galaxy, and I know what's going on over its entire light curve, can I get some more information there? And we can start folding all these tools in and all the different explosion modeling efforts for the various astrophysical transients that are out there. And hopefully we can come up with a thing that will not only allow us to analyze these objects with less data, but also tell us when there's something truly interesting that we need to trigger follow-up on immediately. Because it's something new and exciting and something that we haven't seen before. And so that's where I'm thinking all of these tools are going. And of course, once you start getting to these numbers, you can no longer have humans in the loop. So all of this follow-up is going to have to be triggered automatically. And so that is the next big challenge, is how do you build something that can tell you this is interesting astrophysically because it looks like nothing I've seen before, and I need to trigger this telescope with this resources immediately and not have a human in that loop. And so that's where I think we're going. And with that, I will stop and take any questions.
That's great, Peter. Thank you. So there are no questions in the Q&A tab just yet. So I'd invite people to enter their questions there, or they can raise their hand as we've discussed before. So look for the emoji at the bottom of the screen. I was I had to chuckle a little bit when you were talking about the citizen science work with Galaxy Zoo and the correlation with closing up times in the UK. Do you think, well, just based on that, there's a more serious point. Do you think there's any space left for citizen science in astronomy these days, given how well machine learning can perform and the kinds of tasks that it's usually being used for?
Yeah, so I think with any of the things that we're building, there's still a potential role, although it gets more complicated, the more interesting tools that we develop. So one of the things, of course, we've seen with, if you're looking at any of the latest ChatGPT 4.0, whatever, they hallucinate, okay? And if we're starting to rely on some of these tools to do things for us, it would be great to see when they work and where they don't. And I think citizen scientists may be a way to tackle that problem. So I think there's a role. I think some things are getting minimized because of it. But any next big thing that we push on in astronomy, I think there's a path for a period of time where we can use that. The thing with most, I think a lot of people don't realize, is how much art there is in doing machine learning. And because of that, it opens up a large chance to fail or find what you are expecting. And I think a lot of the great science now is going to be focused on finding things that we haven't seen before. And so that's where we need to have people come up with models, test programs, have humans go through, validate this. So I can see some role there.
Okay. You raised some interesting points that may come up in the panel discussion as well, especially around ChatGPT. Are there any questions from the audience? Okay, yeah, there are a couple just appeared. So HiEpNV asks, well, they say, thanks, Peter, for the great talk. When fitting the radiator transfer results to a supernova spectrum, is it a kind of Gaussian fitting? Can you elaborate a little bit more on fitting using the emulator?
Yeah, so what we're doing here simply is an L2 norm. And so every spectrum that we take, we of course put it on the proper flux scale given its distance, and we assume a cosmology for that. So there's a slight uncertainty with that. And then of course there's the signal to noise of the spectrum itself that has an uncertainty as well. And then literally we take the TARDIS generated emulated spectrum, and it has its uncertainties like I was showing you there based upon how well TARDIS can produce these. And literally we're doing an L2 norm between those two data sets, and that gets our ranking, and that's how we go through and filter out that probability space.
Okay, Emma.
And then, I should mention, he was fitting 10 spectra simultaneously there. I just showed one of them, but he was fitting the entire time series of spectra when he did that.
Okay, thanks, Peter. Emma Rath had a comment and a question, so she thanks you for the great talk and sharing the history of it all. But her question is, will you run the various possible models on every observation, and then the observations that don't fit any models are the interesting observations to get more spectra on immediately?
Yeah, so that's the interesting challenge, and that's a really good question, because we need to figure out both the problems. So we will have the ability to get some spectra that is going to be coming off of Rubin and the large survey of space and time. And so when we do that, there was a cost associated with that, and we want to maximize the value of that observation. So I think automatically running an analysis of that spectrum is critical for us to maximize the scientific value, because as you said, if it's something that's not fitting what we expect, then clearly we're going to try to trigger more observations. I will tell you, in the Palomar transient factory, we had discovered and spectroscopically typed over 1,000 supernova. By the time we found a supernova spectrum which did not match its light curve, a type 1a supernova, and it became one of these weird subtypes that's out there now. But basically, given the light curve of the supernova, we thought this was an entirely normal type 1a supernova, and the spectrum didn't match. And we actually had to wait until all of the data was reduced and the spectrum was reduced, and we saw this months after the effect. So the thing had come and gone. We could do nothing about it anymore. And yet we discovered an entirely new class of supernova. If we had been able to analyze that data, by the time the supernova hit maximum light, we would have absolutely been able to tell this was a clear oddball, and we could have triggered a whole bunch of other observations. And so it's things like that you really don't want to screw up moving forward.
Hey, I guess this is more of a comment than a question. It echoes what you were saying, Peter, but IV1 comments that data is cheap, but labels, i.e. the ground truth, are expensive, and that's always going to remain true. So I think that speaks a bit to this need for citizen science as well.
Yeah. Yeah, labeling is hard work.
So I continue to invite the audience to add any questions to the Q&A tab, or they can also raise their hand. If there are no more questions, well, first of all, I'd like to thank the speakers for today. And both, well, Peter, Yuan-Sen and Salman have kindly offered to remain and have a bit of a panel discussion. So we've got about 20 minutes set aside for this. It's an opportunity for members of the audience to ask further questions, you know, synthesizing all the information that they've heard today, and prompt a little bit of conversation between the speakers as well. We've heard some we're drawing from different areas. We heard a lot about cosmology from Salman, We've heard about transient science from Peter, and we've heard a kind of a holistic approach using large language models to all of this from Yuan-Sen. So I think there's some interesting kind of crosstalk to be had there, but we'd also like to hear if there are any particular points that the audience would like to return to. Okay, Peter, you mentioned ChatGPT and large language models and how they can be used, or how citizen science can help with that. But we also heard a lot about large language models from Yuan-Sen, and I'm wondering whether you could talk about like maybe you can have a little bit of discussion around that point, where the need and the utility of these models are going to come in. So maybe Yuan-Sen, you'd like to comment first on what Peter was saying?
Yeah, I guess it's just yeah, I guess depend on how strong the not just the LLM, so the VLLM, the vision large language model. So some of the tasks is more fuzzy, but there are rules to be followed, right? So in those cases, I can imagine some of this VLLM will be a very good citizen scientists themselves, with like either some rules, some iterations, some interacting with the data. And that could be quite interesting. I think it's like pretty low hanging, and just yeah, actually, like there was a paper that came out yesterday where people just use like the GPT 4.0 to do the classification from zero shot, right? So I can imagine some of the very like basic tasks, the initial version of Galaxy Zoo can be done with VLM. But of course, as things become more complex, the VLM is far from being like human-like. There are lots of things that when I try to play with that, is still fundamentally weak. Like even like simple things like reading the plots is like surprisingly a hard task for VLM.
Yeah, and that's, I think that of course is the next great big advance, right? Is when you can get something that can read a plot,
yeah,
and understand it.
Yeah.
Because some of the things that I could see doing in, say, transient science could greatly use that type of help, which is you're not only giving information about the supernova, but say you have, as we're going to have in many cases in the near future, now that DESI's going, a spectrum of the host galaxy for the supernova. So if you could feed that spectrum and all the information you have into an LLM, and then ask the LLM the question, is this something worth triggering on given this information? That's the type of question you'd like to do, you know, in the future.
Yeah, I agree.
And
I
then
think
just have no humans.
Yeah. So I think the trick here is to have a human label a data set that become a very famous like benchmarking set. Because once you make it like a benchmark, I'm pretty sure like someone will try to beat the benchmark. Yeah. Unfortunately, it's really like surprisingly big, because I have tried that even, and this is like particularly like important for us, like reading a plot, and it's still not done well.
Yeah.
Yeah, this speaks to some of the disjoint between, you know, like people who do LLM or VLLM from what we care about, right? So people, and like there's a disjoint where like people might think we care about like a mathematical reasoning, which is part of that. But I think like at the same time, for low hanging fruit, we care more about things like reading the plots. But that is not often a convey, just because the two fields are quite a disjoint.
And we heard some interesting. Oh, sorry, was somebody about to say?
I was just going to say we have a question from Emma Raptier.
Okay.
Do you
Yes.
see large language models being able to solve problems that a human hasn't yet solved? Right now, no. I don't see. I mean, it's hard to say. Is the question more about will they get new intuition and think about something in an entirely new way? I don't think they're there. Will they be able to brute force a problem? You know, here I'm thinking like AlphaFold and something like that. Yes, they'll do things like that. Is that a true discovery? Is that solving a problem a human can't? I don't. It gets to be a question of semantics, I think, at some point.
Yeah, I think it depends a lot on the type of a question that we are talking about. And yeah, there's an old saying in Chinese that's like 3 shoe maker is better than a zhuge liang, which is like a famous strategist in the olden China. The question is like, if you have 3 billion shoemakers, like can you beat Einstein? And that depends on the question a lot, right? So I don't think
Right.
there are lots of like engineering needed. So the current LLM, the way that I look at it is not smart but not stupid, right? So you need, like, if you break down the question enough, there are many fun pockets of research that can be done there. I don't think, not the human cannot do that, but just I don't think we do not have enough human resources to do that. And that itself is a discovery, right? Like whether or not you can come up with really like innovative stuff. Like we asked that question like a while back, but I think the question is, we do not have a very good understanding on how astronomer or physicists gain knowledge. And that is quite different from mathematics. I think that is a fundamental bottleneck, which I don't have a good answer, because I just feel like the way that we gain knowledge seems too organic, and it's not as structured as mathematics.
So I can say something here. I think part of the problem is that this is a very narrow view of thinking about science in terms of solving problems. Most of the time, I'm not interested in solving problems. There are things that I don't understand, and often I'm trying to come up with models or ideas in trying to resolve some contradiction or something that is annoying me, right? So a lot of the very interesting papers that are out there are actually simple models illustrating a principle, right? Which has some math or computing behind it, but it isn't aimed at fundamentally solving some like messy problem, right? It's just aimed at getting something straight. So this means the LLM has to be creative in a certain way. I don't even want to ask it any problems. I want to go to it and say, entertain me with some science, right? So can it do that? That is not obvious to me, right? I mean, if all it does is be like a very smart grad student, I'm not impressed. If I say solve this problem and it comes back with a solution, I'm like, okay, who cares? That means it was a solvable problem. I'm done. The interesting thing is, can it create hypotheses that make you think? You say, oh, that's interesting.
Yeah.
How the hell did it come up with that? So I think that's a non-trivial kind of scenario. On the other hand, to argue that it's not possible, I think is very dangerous, because this is very early in our understanding. We don't have any understanding of how these things work. I'm sorry, but we do not, right? They're like massive black boxes, completely fed by computation and data and some smart engineering. That's it. So, and we are just relying on massive brute force compute, and they're getting better and better. I mean, of course, there's some intelligence behind what people are doing, but it's not coming from some like super deep understanding of quantum field theory or whatever it is. It's not where we are at. So it's quite conceivable that these things are going to be way more powerful than we think. And a few years from now, the kind of argument we are having would be considered kind of dumb and ignorant, people will say. In fact, we may well be replaced in our jobs, right? I mean, I don't know. So it is interesting. Can they be really creative in an unprompted way almost? That's sort of
that's the real key for science, right?
Yeah, that's the real key.
I'll give an example, very, very simple example. So I was giving a lecture at Berkeley about a gravitationally lensed supernova that we found many years ago. And it was one of those things where I realized if we were able to recognize, this is like the thing, recognize that this was lensed earlier on, we would have thrown a ton of resources at it earlier. And so the question I asked myself was, is there a better way to identify these things with a very limited amount of data? And I came up with a very simple solution for it, which is, well, we could find lens type 1a supernova, because most lenses are elliptical luminous red galaxies. Those luminous red galaxies have great photometric redshifts, so therefore I don't need a spectrum of it. And on top of that, type 1a supernova are only found in luminous red galaxies. The other types of supernova aren't. So if you had a lens supernova that wasn't in that galaxy, the lensing could make it brighter. And so if you see a type 1a supernova that was brighter than it should be, given the redshift that you get, then this is an easy way to find it. That's a very simple type of question to ask. Is there a better way of finding these things? And then the solution turned out to be simple. The thing is, could an LLM think up of an interesting question to answer? And that, as Salman said, now, maybe not, but in a few years, maybe so. And so that'll be interesting to see how that plays out.
Yeah, I would love to just, it's a question that I've been thinking a little bit more, right? So if you dissect, it's a very gross, a characterization. So imagine if what we call creative is a mutation of the current ideas, or the merging of the current ideas. So I think the chances that LLM can come out with is pretty high. It's next token prediction or summarization. The question is, how many of the ideas that we really think are creative, how often that happens? And I think that is particularly rare, like even in the human race. Like a lot of things that we are doing is very incremental.
I mean, if you look, like, and I know it's not a great way to judge science, but if you look at the Nobel Prizes, right, half of them or more came about just because people built better instruments and discovered something that they weren't able to see. They had higher precision, and the other half were creative ideas, you know, and so they're not that often. And you know, I talked about Chandrasekhar. That's a prime example. The Chandrasekhar mass came about because you put special relativity in with quantum mechanics, and a very simple idea to merge those two fields, but nobody had thought about it, and it completely revolutionized the way we think about stellar evolution. And so the question is are there things out there that you could go after, low-hanging fruit, you know, that could synthesize those things? And until you can read a plot.
Yeah. Well, sure, but I mean, imagine that LLMs get a lot smarter, and then in a way our prompting them becomes like prodding them. We kind of annoy them and say, hey, listen, you know, and we poke them, and they say, okay, you know, shut up, I'll come back to you with some smart just to stop you from annoying me. And you know, I'm actually not convinced at all that that you can't make an, I mean, LLM is a very loose term for, you know, some large AI model, but I think there'll be a very sophisticated notion of prompt engineering that we, you know, much more than we have now. We could get something creative, and also a lot depends on what it's being trained on. Like the point I was making is that if you train it on a very limited set of things, and it'll think, it's very hard to generalize, you know, beyond that limited thing. But if you say, let's just, you know, put all kinds of stuff in there, you know, you don't quite know what it's going to come up.
Right. Like on the practical front, right? Again, if you can come up with a long list of what you think is creative, like you say, the Chandrasekhar, like this thing, like this list of things, if you can see through all these things and say A plus B like equals to C, then you can start to check that. And even for human, it's hard to come out that like with that long list. And if we can get that, then we can start to ask the question, because now we are asking a question we would not know the answer. I would love to think that it's possible. My feeling is that it's possible, but I don't have a way to prove or disprove that.
Okay.
Question from Ivy Wong.
Yeah, I think we've got time for one more. So, do you want to read that out, Peter?
Sure. So following your comment, Yuan-Sen, about the challenges of reading a plot, exact calibration from machine learning, deep learning models can be challenging. How does the panel suggest we address this?
You need the human a labeler. You still need some form of that to either benchmark or fine-tune the models. Just hard to avoid that. I think the hard part is, like, as you go to science, the human laboring costs become too high. And this is why we are not doing that good in science. I don't think it's not LLM like cannot scale to that. Just that most of the benchmarking, they are really just for practical reason. Like, there's no way you can ask 20 or 100 professor to sit down and write question for benchmarking. But maybe we should.
I actually think that's probably not a bad idea. So I'll tell you a very recent example of what we did for this is we applied many layer CNN to do that transient classification. Is it real or bogus for us? Because we thought, well, let's give it a try and see how it works. And we tested it against this data set that we produced for it that had 800,000 objects in it. And student did it, ran it, and found about 8,000 objects where we either said it was bogus or we said it was real, and his CNN was saying it was the opposite.
Right.
And I was like, man, this is really confusing. And so I went and looked at all 8,000 objects. And it turns out that two assumptions we made were wrong when we gathered all this data. The first assumption was that we knew where all the supernova were and that anything else was garbage. That turned out to be wrong. We missed some supernova and the CNN found it. And the other assumption was anything that we labeled as supernova, because we'd seen it going up and down, was always a good object. And that turned out to be wrong, because sometimes you get a bright asteroid to go by it and it saturates it and it creates what is garbage. And so I went through and relabeled 8,000 objects. Now, fortunately, that only took me 8 hours. But, you know, like you said, when you push to these next level things, well, maybe getting 1,000 PhDs to look at these things to help us with the fine tuning is the way we make the next discovery. But yeah, I can't think of any other better way of doing it now, but at some point, well, this goes into the Skynet views and they'll start training themselves. So
yeah, I think Yuan-Sen actually alluded to something that could be done by using a whole bunch of different models trained very differently on attacking the same problem. So they can actually, by using model mixtures in effect, you can get more reliable results. Of course, nothing, I mean, it'll still be some vague square root of n kind of scenario, but it is kind of interesting, and they can learn from each other. They can say, wait a minute, you know, you say this, but why? And right, in their own way, you know, they can figure this out. So I think by essentially a sort of adversarial approach, you know, generalized adversarial approach of this kind is probably going to be helpful in these kinds of problems.
Yeah, it has also shown to be quite powerful, even just like within the computer vision, like this type of like bootstrapping from itself.
Yes.
And of course, the initial few round will be super expensive, and this is why people will be deterred, because it seems like the few iteration will be like you don't see the obvious gain as fun as just looking at a supervised learning. You just a bunch of model chit chat, and most of the time they just speak rubbish, and you find you're wasting tokens, but you might not be. right? So the bootstrapping is really about a trade-off about cost. And I think there are lots of opportunity for like sufficient, even with sufficient inference time, you can do a lot.
Yeah, I mean, it is expensive. I mean, as Yuan-Sen was showing in his slides, I mean, one of the things we don't appreciate is how much computing goes on behind simple queries that we put to GPT-4.
Yeah,
Actually.
yeah.
Mhm.
Okay, there are no more questions from the audience, although if anybody wants to chime in at this point, feel free to do so, but we're coming to the end of our 20 minutes panel discussion. So I suggest we wrap it up there. That was a really interesting discussion. Even though we only covered a couple of questions, they were really, really stimulating. So I think that now brings us to the end of this fourth Intersect NCI showcase for 2024. I'd like to thank our excellent speakers today. They've taken time to share with us their fascinating research, their extensive expertise, and some very exciting results. I'd like to thank the audience for engaging with the showcase and for the stimulating Q&A. I'd like to thank Intersect and NCI Australia for their support for this event, Mei-Yun Chang for her hard work organising the event, and to the Intersect webinar team for their behind-the-scenes effort. So thanks all, and goodbye.